Drjs is a JavaScript library for dimensionality reduction where we implemented 11 DR methods. A typical use case for Drjs is a web tool using DR. You just need to import Drjs, create a DR object, and then call the transfer method. That's it. See the talk, the paper, or the supplemental material for more information.
Magnetic reconnection is a ubiquitous and complex physical process that occurs throughout the universe. Locally, this process is observed when the solar wind interacts with the Earth's magnetosphere, causing magnetic field lines to break and reconnect. One of the results of this process can be seen from Earth as the aurorae. In our talk, we introduce scalar field topology as a method to identify and analyze features in 2D magnetic reconnection simulations.
Transitions are widely used in data videos to build seamless changes between video narrative. As the attention cue, they can not only keep viewers oriented but also express narrative information. After conducting a content analysis on the transitions in the dataset, we provide a comprehensive taxonomy of narrative transitions in data videos.
This is a picture of a Tableau visualization within the browser. The data behind the visualization does not exist here, and Tableau is not running. This is just an image. However, parts of this image are fully interactive. Please join our presentation to see how we can share interactive visualizations across the web, free from any dependency on data or visualization application.
A testing environment for continuous color maps. Many other fields in the computer science do it, we should do it too. With our work, we introduce the approach of using test functions as a standard evaluation method. We present a test suite for continuous color maps implemented in the CCC tool. Adapt the test to your requirements at the interactive testing section and observe them at the testing evaluation section.
Information about vulnerabilities helps defenders prioritize what they need to patch, but this information can be difficult to interpret. In this paper, we support interpretability using a focus and context approach to visualizing vulnerability data, including a clustering overview, plots that enable filtering based on severity, and explanations of text features and descriptions. We invite you to read our paper to learn more.
We present the first generic design space and library for visual piling. Inspired by physically piling paper documents, visual piling describes an interface for spatial organization of visual artifacts into piles of partially overlapping items. Piling affords interactive grouping, arrangement, previewing, browsing, and aggregation to reduce the complexity and support comparison of large collections of small multiples.
Hello. Student competition is intrinsic to the pedagogy of cybersecurity education. At RIT, we have observed that the collegiate penetration testing competition and other related competitions are missing a key element, visualization. In this position paper, we provide an architecture and plan to create compelling experiences for participants and spectators. In doing so, we can potentially attract new talent into the field.
Ray tracing techniques can create images of astonishing realism and beauty. In the last years, the performance of those techniques has been increased significantly using dedicated hardware. Who thought that it's also possible to accelerate this? We show how to dramatically accelerate force-directed graph drawing with RT cores, yielding a speed up of 4 to 13x. If you want to know more, please see our talk.
Programmers often make mistakes like this. ABS function is incorrectly called with a string. A programming language can catch such mistakes early on, but for this, it needs a type system. We present Typical, an interactive visualization tool for programming language designers. Typical allows them to explore common function type signatures and helps create a type system.
Asteroids have always been and will always be a threat to life on Earth. Most likely, an asteroid will hit deep water, but what properties will actually lead to a threat like a tsunami? Ensemble simulations are a common tool to understand the effect of different parameters like the size of the asteroid. We propose an interactive visual approach to help analyzing deepwater asteroid impact simulation ensembles.
Deep learning models have become ubiquitous, but we often lack interpretations for their decisions. We developed a visual analytics system to interpret models that perform multi-class DGA classification. For each layer of the model, we visualize clusters inside its activation data, showing how classes and clusters relate to each other. In addition, we provide a decision tree to explain how these clusters are constructed.
We asked participants to recreate bar graphs. When the bar was alone, we saw a different pattern of error than when the bar was presented with context in a stacked bar graph. We found that absolute error increased for higher bars when they were presented alone. We also found that there was a bias in the responses such that they were repulsed from an implicit 50% mark. We found a magic number, 10%, to predict error. Participants are usually within 10% of the height of the bar.
Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster. Connect to the data you care about. Sort, highlight, drill down, or filter your data in seconds. Add calculations to extend your data. With Tableau, you can keep on asking questions in the data until you discover the root cause. Tableau. Answer questions at the speed of thought.
We present a flexible and easy-to-use software infrastructure for interactive rendering of large-scale display walls, either from on-site or from remote cluster. The display servers can easily be configured to support a range of typical network and display hardware configurations. The client library provides a straightforward interface for easy integration into CPU and GPU renderers. We also demonstrate this framework for use in deploying low-cost alternatives for display walls.
After determining the departure timestamp, the experts then moved to verify the recommended shuttle stops and routes. Note that Shuttle VIS recommends the default shuttle stops and routes based on the metric of average distance. Then they observed that in our cluster 4, the system recommends Hejianjianyuan as the shuttle bus stop, but the experts identified that another drop-off spot Panshanhuayuan is located in the middle part in this regional cluster.
Predictions made by machine learning models can be hard to understand. Counterfactual explanations explain model predictions by telling the users how to obtain the desired prediction with minimal changes to the input. We introduce Drjs, an interactive visualization system that supports counterfactual-based explorations on individual instances and data subgroups. Please check our paper for more details.
In this paper, we investigate design choices for Choropleth maps by domain experts. We tackle 2 research questions: how do domain tasks influence the design choices, and what equal error projection is preferred. Through a survey, we collected 40 Choropleth maps designed by 20 social scientists, and our analysis suggests that the choices vary across tasks, the projection was most important, and the equal error projection was preferred.
VIS is a visual support system for the development of visualization algorithms. It has live compilation, automatic version control, predefined interactions, and tools for visual parameter analysis. By displaying the complete history of the algorithm, users get insights into the correlation between source code changes and visual differences.
Interacting with large datasets could be painfully slow. We can reduce the latency with faster backends, but that's not always attainable. Here, we investigate a solution that only leverages techniques on the front end. We propose interaction snapshots, where users can view the results at a later time. We found that users experienced much less frustration and were able to complete the tasks faster.
DVR has always been from considerable interest to the scientific community. To this day, traditional desktop setups are the gold standard. However, what if we could utilize DVR in virtual reality? Now you think, VR and DVR are so computationally expensive, how is this even feasible? Come to my talk and we present you a straightforward solution to visualize volumetric datasets with high refresh rates on VR devices.
Imagine you have tons of text data to analyze. And you want to get an overview of your data, but traditional topping modeling techniques such as LDA are not working for you. Then, why don't you try Architext? We introduced a scalable and flexible way to interactively build hierarchical topics.
A Morse-mean complex is a topological descriptor that captures the gradient flow of a scalar function. The best-known approaches for its computation incur large runtimes for bigger datasets. We address this gap by introducing the first completely GPU parallel pipeline, which achieves speedups of up to 7x, with our individual algorithms attaining speedups of up to 129x and 4.5x.
In this talk, we introduce CallFlow, an interactive visual analysis tool that provides a high-level overview of performance profiles from large-scale scientific applications. CallFlow visualizes the flow of resource of a program execution as a Sankey diagram to detect performance bottlenecks in parallel codes. CallFlow simplifies these calling context trees based on semantic information by constructing supergraphs.
How do you visualize the nanoscale, 1 billionth of a meter, for the public? As part of a Science Center exhibition, we developed an immersive environment that explains nanoconcepts by allowing users to explore nanoproperties. We reflect on how exploration, the confluence of explanatory and exploratory visualization, can be applied to visualization in public spaces.
When developing a deep learning model, people typically struggle to optimize hyperparameters that affecting the model performance. To relieve the pain of this manual trial process, AutoML has been developed as a solution. However, to maximize the potential of the AutoML, people should identify a good AutoML setting for their task. Hypertendril helps to maximize the potential by visualizing AutoML algorithm behavior and guiding effective hyperparameters.
Evaluating alternative interpretations is an essential part of complex sense-making, but the resulting ambiguity is rarely considered in the design of visual analytics systems. Avalanche forecasters rely on sparse and human-produced data to assess avalanche hazards, often resulting in ambiguous interpretations. We used simple glyphs and unit visualizations to specifically consider and support ambiguity in the avalanche forecasters' sense-making processes.
Scatter plots and parallel coordinates are widely used for visualizing multivariate discrete data. However, for multivariate continuous data, the continuous scatter plots and continuous parallel coordinates are more suitable. In this work, we extend them to uncertain data. Additionally, we also extend fibers to uncertain data. If you are interested, come to our presentation.
Pixel Clipper allows visitors to quickly and expressively extract visual clippings from visualizations and add comments to them. The clippings are useful for engaging the public with complex datasets because they are entry points into the visualization. This can be applied in a wide range of engagement experiences, such as the use of facilitated and ambient displays at public engagement events.
While meetings are an essential part of everyday business life, most calendar visualizations are not designed for retrospection. We present a tool consisting of 4 coordinated views that integrate into the user's daily workflow and are designed to promote self-awareness about past scheduling decisions. We discuss the insights gained from an internal user study and from a field deployment. We also discuss how we strongly inherit from the principles of personal visual analytics despite targeting a professional environment.
We present a method for real-time ray tracing of stream tubes for fluid flows and diffusion tensor MRI. Rays are traced through a sparse voxel lock tree until they intersect leaf nodes which contain tube segments. This checkerboard pattern indicates voxel boundaries. Within leaf nodes, we can ray trace straight tube segments or ray cast curved tube segments.
In this study, we designed a system named Causality Explorer to facilitate the causal analysis. Users can explore the causal graph to perceive the causality and its uncertainty, validate the causality with the raw data, and apply the confirmed causality to what-if analysis.
Forensic investigation of file system metadata is a difficult and time-consuming task that requires deep expert knowledge. Following a user-centered design, we implemented an analytical tool to guide analysts during a security incident investigation. The evaluation proved that the tool could significantly improve the efficiency of disk exploration, even for less experienced analysts.
Analyzing urban heat island phenomena, which cause higher temperature in cities, requires to explore the relationships between climate and urban morphology. In an ongoing co-visualization framework, we propose different ways to visually explore both urban and climate data at a city block scale in order to support the analysis of urban heat islands.
We propose a new semi-automatic method that uses topological features to guide users in tracing neurons, and integrate this method within a virtual reality framework. We use the Morse-Mel complex to find a set of candidate neuron arcs. The candidate arcs are integrated into a VR neuron tracing system and exposed through our Morse-Mel complex guided semi-automatic tracing.
Morning, good afternoon. Welcome to our color theory and applications. And my name is Francesca Samsel, and I'm here with 4 other folks who work in color, and I'm going to ask them to introduce themselves, and then we'll give you a brief overview of what's happening in the session. And know that we're a little tight, so there is time for questions after, but if you have more questions, there'll be breakout rooms in the second half, and you can ask them then, okay? So, Danielle.
Hey, I'm Danielle Szafir. I'm an assistant professor at the University of Colorado Boulder, and a lot of my research with regard to color is looking at things like color perception, thinking about how does color behave differently in visualizations than it does in other media, and also thinking about how we can use perception and automation collaboratively to drive design and encourage better color practice. So I'm going to be talking a little bit today about some work we've done in terms of modeling discriminability and also in terms of tools that help people more readily generate continuous color encodings. So looking forward to working with you all.
Hello, my name is Karen Schloss. I'm an assistant professor in the Department of Psychology and Wisconsin Institute for Discovery at the University of Wisconsin-Madison. My lab focuses mostly on visual reasoning, so how people infer meaning from visual features like colors, and how we can use that to make visualizations that are easier for people to interpret. So my earlier work has focused more on color aesthetics, so why we like the colors we like and how we like colors and color combinations. And that's a lot of the work that drove Cologorical, which is the tool we're going to be talking about that I'll be sharing today. And so that's some of the earlier work that I'm doing, and moving forward, we're focusing more on semantics, so how we can make visualizations easier to interpret by incorporating concepts.
Okay, Pascal, and people should mute because there's an echo.
Oh. Hello? I'm now in. Hello? Oh, okay. Hello, my name is Pascal. I'm a PhD student at the Latin University, and I work at the CCC tool. And we created the CCC tool to enable the creation of color maps, and also the analyzation of the color maps. Yeah.
Hi, I'm Stephanie Zeller. I am on staff at the Texas Advanced Computing Center, and I'm really interested and have been working on sort of color in scientific visualization for increased discriminability, semantic understanding, and better exploration and attention direction in sort of large data sets. So happy to be here. Happy to see everyone.
We can start the video, the intro video.
Good morning, or good afternoon. I'm not really sure, as this is pre-recorded. So my name is Francesca Samsel, and I'm a research scientist at the Texas Advanced Computing Center at the University of Texas at Austin. And I've come together with some of the other folks in the field who are doing some really interesting work in color and color tools for scientists. And I'll let them introduce themselves in a moment. But I wanted to give you some context of what brought us together and why we're doing this tutorial. The first thing that we realized was there are several new visualization tools that have come online recently, and they all have different strengths and weaknesses, and good for this kind of usage, not so good for that kind of usage. But for someone looking for color tools and color usage, it's kind of a high bar to wade through all those tutorials and sort through what is best for what uses. So given how many new capabilities there are, we thought that we would start, and it's a start, with a tutorial laying out of 3 or 4 actually, I think in this tutorial, of the newer tools online, and give you some demos so that people can see what their capabilities are. And then just take a step back and think about where are we as a community that works on color for visualization, and what are the next set of needs that, that people might begin to address. So more specifically, in this tutorial, we're going to discuss theory and usage of color encoding design for visualization, including state-of-the-art strategies and tools. There are several new color palette and color map construction tools such as Cologorical, Color Crafter, Color Moves, CCC tool that have recently been released. So this tutorial is designed to help participants understand their features, strengths, and constraints in order to enable a selection of the tool that best aligns their needs. But first, we discuss the principles and decisions and mechanisms for designing effective color encodings and then explore these tools in hands-on sessions, creating color palettes and color maps and testing them on data. We will close with a discussion of how future tools may aid in the open challenges for using color in visualization. First half of the tutorial think of as grounding us in principles and processes. So we're going to have some discussions and presentations on color discriminability, color cognition, and artistic color theory and color interaction, and how those all impact scientific visualization in the way that we absorb data. And then the second half of the tutorial is hands-on, and
we need to be rolling the video on our end, or
the first section will review Cologorical and color crafting, and we'll provide an overview of them both. And then
the videos just run sequentially, please.
Guidance and data for you to try them out for yourselves. And then the second half of
the
second part of the tutorial, we'll do a quick overview of color moves and a little more in-depth dive of CCC tool, because that's a pretty sophisticated and has more capability than some of the others, more complexity, so that you'll get an understanding of its capabilities.
All right,
and we will also
thank you so much. Sorry,
on
virtual conference
visualization for participants to work on themselves. Lastly, we'd like to acknowledge that these are just a few of the tools that have come into fruition lately, and there are many others and other very valuable assets that we have not had time to cover, but we look forward to your discussion. And as we said, then we'll follow up with some discussion of the whole direction of the field.
My name is Danielle Szafir. I'm from the University of Colorado Boulder, and I'm going to start off today by talking about some of the basic principles of color discriminability. That is, how do we know that we can detect differences in our data? To illustrate this challenge, I'm going to use a quick example. So, how many categories of bars would you say you see here? My guess is you see 3 equal greens, so you think there would be 1 category of bars. However, we can easily manipulate the differences between the colors of these bars to, for example, change the lightness or change the hue, and be able to detect and distinguish different categories that might emerge. And changing these values and allowing us to detect more categories is an example of discriminability. So when we're talking about discriminability, we're really talking about this question of how well can we distinguish between a set of data values. Core to this idea of discriminability is the concept of a just noticeable difference, or JND. A JND is the smallest color difference that can be reliably detected. Granted, this depends on your definition of reliable, but typically speaking, reliably detected means that it's detected between 50 and 75% of the time. In the context of data visualization, when we're thinking about JNDs, we essentially want the smallest critical color difference between any 2 values to be at least 1 JND in size. So that is, a JND corresponds at the very least to the smallest important difference in our data. One key thing I would like you to notice here is this idea of color difference. Color difference inherently speaks to a mathematical relationship between any 2 colors in our visualization. And that's really what we're going to focus on in our discussion of discriminability during this tutorial. I'm going to focus on this idea of discriminability over 3 different topics. The first of these is color spaces. How do we define the mathematical attributes of a color? From there, we'll move on to thinking about differences. Once we've translated a color from the thing we see to a set of mathematical values, how do we understand the differences in those values? And I'm going to close by talking about some unique challenges for considering discriminability in data visualization. When I use the term color space, I really am talking about a way of mathematically defining color. One of the most familiar that we have is from physics, where we talk about this idea of wavelengths. So any number on our wavelength scale corresponds to a very specific color. However, folks who've used color in practice know that any single number is not necessarily a very rich way of thinking about color in the ways that we use it in visualization. We need to consider other factors like what is the saturation or what is the lightness of that color. We can draw on a variety of traditions to reason about the important aspects of color for creating effective visualizations. In particular, we can think about the ways that computers represent colors, the way that psychologists reason about colors, and the ways that artists design with colors in order to create effective visualization. And one of the interesting things that manifests from all of these different color spaces is that they actually correspond to different components of the construction and use of visualizations in practice. We build visualizations on computers, we see data encodings based on principles from psychology, and we design visualizations using ideas from art. So in practice, we care about all of these different ways of thinking about color. I'm going to start with the computational representation of color that's used in computer graphics and used by our monitors, and that's this idea of sRGB. So the RGB cube has essentially our three primary colors, which correspond to the primaries that we have in our monitors. So this is our blue, our reds, and our greens. In a way, this simulates what is going on in the eye, where we have our short, medium, and long cones that serve as our photoreceptors in the eye. So while this feels like it should be a very intuitive and very perceptually useful space, in practice, RGB is not perceptually uniform. We might see bigger or smaller steps in the data corresponding to equal size steps in RGB. And you can see an example of this here. So each of these rectangles has an equal distance from each other in RGB, but we have a much harder time distinguishing the greens from one another than we do the blues. So what this tells us is that equal distances in RGB are not equal to equal perceptual differences. One of the questions that we might start to ask based on this observation is, how exactly do we see color? And this gets to the basis for many psychological models and color spaces. In psychology, we have this idea of opponent processing theory. The basic idea here is that we have receptor cells in the brain that take the input from our rods and cones and process it in systematic ways. And these ways correspond to different color opponency pairs. So we have how much black or white is present, how much red or green is present, and how much yellow or blue is present. One logical conclusion is that if our eyes and brain, so our visual system, process color using these opponency pairs, maybe that's a useful way to represent color in a way that aligns with the perceived differences that we see between color values. And this is one of the fundamental ideas underlying CIE Lab. So Lab has three axes: lightness, or L, how much red or green is present, or A, and how much blue or yellow is present, or B. And the A and the B plane essentially form a hue and saturation plane at each level of lightness. One of the nice things about CIE Lab is that Euclidean distance in CIE Lab is intended to be perceptually meaningful. CIE Lab is what we call an approximately perceptually uniform space. That is, our perceived difference in colors approximates our perceived differences in data. So a larger difference in color would correspond to a larger Euclidean distance in lab, would correspond to a larger data difference. I think it's pretty intuitive how this is useful for visualization. However, in practice, CIE Lab does provide an imperfect representation of the ways that we see color. And CIE Lab was actually originally designed in 1976, so color science has had a lot of time to improve on the CIE Lab model. The most recent standard in color science is the CIE Camo2 model. And what this is essentially designed to do is provide us with a more precise representation of how people perceive colors. So for example, in the sunburst diagrams here, a perfect perceptual model would align all of the dark and light blue squares and would have essentially a perfect starburst pattern where we would have equal sized spokes that are perfectly straight lines. And while you see a little variation in both models, so here CIE Lab is on the left and CIE Cam is on the right, you can see that the alignment and the spokes in our Cam model form more of this ideal sunburst pattern than what we see in Lab. And what that tells us overall is that it's a more perceptually precise model. In part, Cam succeeds because it has a more sophisticated consideration of things like the colors around a particular target and other kinds of contextual factors. As a result, CIE Cam ends up being very complicated in practice. There are implementations that you can use for visualization. For example, Connor Gramazio has developed a package in D3 for using Camo2. But a broader problem with both Camo2 and Lab are that they are both somewhat counterintuitive to work with. We don't necessarily think of designing colors as a function of how much red or how much green there is. And this takes us to this idea of how do artists think about color. So when we're thinking about the ways that we reason with color in design, we think about things like luminance, how light or dark is a color, saturation, how dull or bright is it, hue, is it red, is it green, is it orange? These are more intuitive ways of reasoning about color that map really well to a lot of what you will see in color encoding design in practice. And art offers us a number of spaces for computing these kinds of relationships as a function of these more intuitive parameters. A more accessible way of reasoning about color according to lightness, hue, and saturation is the idea of HSL or HSV. So these two spaces provide us with a redistribution essentially of RGB that allows us to think about, instead of reds, greens, and blues, how much lightness, how much saturation, and how much hue is present in a given color. So this can be a really nice way of modeling and designing colors, but it suffers from a lot of the same limitations of RGB, and that it is not perceptually uniform. One compromise that we can make if we're reasoning about color spaces is we can actually express CIE Lab using polar coordinates. And this is a color space called CIE LCH, or you will occasionally also see it as HCL. So when we're thinking about LCH, we still have our lightness axis, but we also have colorfulness and hue. So colorfulness is a proxy for saturation, and it's expressed as the distance between our chosen color and the lightness axis. And then hue is the angle around this polar circle. So to summarize our discussion of color spaces, we often will use artistic spaces such as HSL or HSV to design a color encoding because these are intuitive ways for humans to reason about color. We can then interpolate these colors using perceptual spaces. These spaces will allow us to match the perceived difference to our data differences. As I mentioned, a key idea behind discriminability is that the differences between two colors are meaningful. And in order to start talking about the differences, we have to move beyond just the representation of color in a particular space to look at how do we then compare colors in those spaces. Perceptual distances allow us to compute difference values that correspond to the actual differences we see between colors. In visualization, what this means is that we can map larger data values to larger perceived color differences. In other words, the difference between our black circle and white circle should be computed as significantly larger than the difference between our black circle and our gray circle. Among the most popular difference equations that we see in visualization is CIE delta E. So delta E corresponds to the Euclidean distance between two colors in CIE Lab. The basic idea with delta E is that one delta E should approximately equal one J and D, or one just noticeable difference. Euclidean distance is simple. It's fast and it's intuitive to compute, and it's intuitive to translate into meaning. I know that a larger Euclidean distance means there's more distance between 2 points, and that the relationship between those distances should be linear. Well, delta E is used very commonly in visualizations. In practice, it's subject to a number of limitations. One of those key limitations is that the real world is actually too noisy for one delta E to be large enough. And this is a problem with all of the color difference equations we're going to talk about. They're all modeled on this idea that we have a perfect observer exploring data on a perfectly calibrated monitor in a perfectly isolated environment with no ambient light, no ambient noise, all sorts of factors that aren't a function of reality, where we have different brightness levels and different calibrations on our monitor. People are sitting at different distances. We're often looking at really small marks on the screen, which I'll talk about in a little bit. And we have all sorts of residual lighting and other factors that might influence our perceptions of different colors. One of the more nuanced issues with delta E, however, is that it tends to fail with saturated colors and with very large color differences. I'll talk about large color differences in just a bit, but when I'm talking about differences in saturated colors, if you look at the two circles on the left, those circles represent a dark red and a dark blue that are both highly saturated. That pair of colors generates a delta E of 10. So does the pair of yellows on the right, where we have the bright yellow and the more goldenrod color. Those two sets of circles do not appear to be equally distant from one another. And this is a broader problem within CIA Lab, where, again, these large saturated colors can lead to misleading delta E scores. So delta E was developed in 1976, and color science has had a lot of room to improve since then. Delta E94 was developed in 1994, and it essentially adjusted for saturation using empirically derived weights. In other words, we take our Euclidean distance function and we weight our L, A, and B scores differently as a function of the actual perceived distances in those colors. So delta E94 gives us a more precise version of perceived color difference. However, it's subject to limitations in that it often mismanages perceived lightness. For example, while the green dot here is closer in perceived lightness to the white dot, in delta E94 it is equally distant to the black dot. So this suggests that we have an issue with the way that delta E94 is handling lightness differences. And in 2000, CIE introduced the delta E2000 model, which offers improved lightness weighting from delta E94. But as you can see in the equations used to derive this distance metric, things have gotten fairly complicated. And when it comes to building interpolations and starting to think about encoding design, using these delta E2000 functions starts to become a lot more difficult and a lot less intuitive to work with, and potentially computationally prohibitive depending on the kinds of operations we're working on. So in practice, CIE delta E tends to be good enough for most visualization applications, and it tends to be much simpler to reason over. And much of the precision that's actually added by the sophisticated differences that we see in the delta E94 and the delta E2000 models actually tend to be mitigated by external confounds. For example, we don't have perfect monitors, which can actually distort the colors that we see and reduce some of the differences between our colors. And some studies that we've done in the past actually show that these differences may be enough to get rid of several of the benefits of using delta E94 in practice. Also, color encodings and visualization tend to rely on lightness steps. We have this notion or this guideline around lightness monotonicity being a good way of helping people discriminate between data values. And we also tend to encourage minimizing hue steps in many cases. For example, if I'm designing a sequential ramp, I tend to privilege changes in lightness over changes in hue. And so these simpler models like delta E can actually do a reasonably good job of approximating those kinds of limited and very controlled differences. There's one key caveat here, and that comes with very large color differences. So if I were to ask you which is a greater difference between the colors, the green and the blue, or the purple and the red, there's not necessarily a good and meaningful way of reasoning about that in delta E. It's not intuitive that delta E should be larger for green and blue or larger for purple and red. At these larger distances, things like we would use for categorical data, color difference takes on a different meaning, and we instead start to think about the more cognitive associations and cognitive distances between two colors. One of the best models that we have for working with this in visualization is the color naming model that was developed by Hero and Stone in 2012. So the basic idea behind this model is that colors that have different names are easier to discriminate and easier to cluster with one another. If you think about your Gestalt principles, if I have light greens and dark greens, those colors are going to appear more similar to one another than if I have light greens and light blues. So this color naming model is intended to model how people assign names to colors based on their CIA lab values. And what we can do is we can look at those mappings and use those to compute vectors of names associated with different colors based on their representation in lab space. And we can use these vectors to compute categorical color differences. This tends to be really useful in things like palette design, as Karen is going to talk about in a little bit, because what this will allow us to do is compute the similarity between any two color values. So both of these sets of differences allow us to reason over how different any two values are going to be perceived when we're mapping data to color. However, visualization offers a series of unique challenges for understanding color discriminability. These challenges range anywhere from thinking about how do I intuitively represent my data to how do these models actually change as a function of the marks that I use, even down to how accurately do I have to follow these models to generate effective and discriminable encodings. Well, when we're thinking about developing sequential encodings, we care about being able to discern fine-grained differences between any sequential pair of colors. That is, the actual distance itself matters. In these cases, we're going to use just noticeable differences and equations like our delta E model to tell us how good our encoding is. When we're thinking about categorical encodings, we don't necessarily care about the pairwise differences between any two colors. We just care that they are sufficiently different. And this is where things like the color naming model can come in handy. Diverging encodings are an interesting hybrid of these two considerations in that we essentially need to use both our continuous delta E metrics and our categorical color name metrics. To break this down a little bit, when we have a diverging encoding, we're essentially dividing our data into two groups. So in this case, we have group A, which is our blues, and group B, which is the reds. So we care about being able to categorically distinguish between group A and group B, which is where our color name model will come in handy. But we care about being able to distinguish the different gradations within each group. And this is where our delta E models will come in handy. There have been recent studies that have shown that color naming actually might be useful for thinking about more than simply being able to distinguish categories. If you're curious about when and why this might be the case, I'd encourage you to check out a paper that Carrie Rita and I have that will be presented later this week. A second challenge when it comes to applying conventional color difference ideas to data visualization is changing geometries. For example, the bars that you see here represent 7 different levels of color difference in CIE Lab, taking into account delta E. As you can probably see, we don't necessarily see those distinct 7 levels, and this is why designers will often manually go in and correct for these differences. However, even after you've hand-tuned for particular differences, making marks smaller or even changing their shape can actually dramatically change the number of perceived differences in our color encodings. And visualization offers a large library of functions for reasoning over discriminability as a function of our visualization geometry. So some basic rules of thumb are that we know that discriminability changes inversely with mark size. As marks get smaller, it's harder to tell the difference between them. And that change levels off as marks continue to get larger. We also know that marks can be more distinguishable when we make them longer. So if I move from scatterplot points to bars, that lengthening process can make it easier to discriminate between my colors. Finally, more recently, we found that discriminability varies as a function of a mark's shape. So for example, it's easier to tell the difference between the two green scatterplot points here when they're represented with filled squares versus unfilled squares. And it turns out that the relationship between a mark's shape and its discriminability can be very rich and nuanced. One last element of discriminability that's unique in visualization is this idea that discriminability needs to be the exclusive driver of our encoding design. So one common fallacy with encoding design is that effective color encodings must be perceptually linear. In essence, this is often taken to mean that good encodings form a straight line in a perceptual color space. For example, if we take our hand-designed color brewer greens here, if we were to interpolate between the endpoints, we would get something that looks like this. And what you can see here is that interpolating endpoints along a straight line in CAE Lab gives us bland and somewhat indiscriminable colors. It turns out that in practice, expert design ramps are seldom linear, and they often have significant variations in terms of the distances between any adjacent pair of colors. So for example, here we have this color brewer greens mapped on the left to our AB plane in CAE Lab space, and on the right to our LC plane in CAE LCH. And you can see that the shapes are not straight lines, and the distances between points actually often vary. In work we presented at VIS last year, we actually analyzed 222 handcrafted ramps, and we saw the same pattern over and over. That is, designer color ramps actually take very interesting and unpredictable paths through perceptual color spaces. What this indicates is that discriminability, while key for understanding how we actually process data differences, is not all that we need to understand in order to use color effectively in visualization. We have other factors like aesthetics, semantics, attention, contrast, all these other ideas that Karen and Francesca are going to talk with you about later in this session. With that, I'd like to wrap up our discussion of discriminability and take a moment to thank the people who have shaped this work and invite any questions that you might have.
Hi, my name is Karen Schloss, and I'm an assistant professor in the Department of Psychology and Wisconsin Institute for Discovery at the University of Wisconsin-Madison. Today, I'm going to talk about color cognition for visualization. There are many factors involved in color palette design. First and foremost, colors need to be perceptually discriminable. So if we can't see the difference between different colors in a visualization, those different colors are not going to be able to communicate different meaning. A second factor is name difference. So if we want to be able to refer to the different colors in a visualization by name, it's helpful if the colors have different names. A third factor is aesthetics. So ideally, we want people to enjoy looking at the visualizations that we are creating. And so there are aesthetic factors that we want to take into account. Another factor is affective impression. So we might want our visualization to evoke some sort of affect or emotion when people are looking at it. And last, semantic interpretation. So each color in a visualization might map onto a different concept. And we want people to be able to easily infer which color maps onto a given concept. So we've discussed many factors involved in palette design, involving perception, naming, aesthetics, affect, and semantics. And the general challenge we face is how to navigate trade-offs between these different factors when conflicts arise. And conflicts do arise in several types of factors, and we're going to talk about some of those today and various approaches to navigating those trade-offs. So to begin, let's talk about conflicts between perceptual discriminability and aesthetics. So here we have our color circle up here. This is roughly a slice through CIE LAB space at a equal L star lightness plane. And so let's say we have a target color that is here. So we've got a greenish color that's our target color, and we want to design around that color. So we're going to bring that over here. So if we want to have high perceptual distance, then what would we do? We would choose a color that's very far apart in this space. So we might choose this reddish color, which is directly across from our greenish color in this plane of this space. But is this aesthetically preferable? Well, if we look at models for human aesthetic preference for pairs of colors, we find that hue similarity is more preferable. Coolness is more preferable, so colors that are in the cooler part of the color space, like blues and greens, and lightness contrast is more preferable. We're not going to worry about lightness contrast for the moment because we're talking about a plane that's roughly equal in lightness, but we'll come back to that in a minute. Okay, so if we think about hue similarity and coolness, how are we doing with this color pair? Well, one color is cool, but the other one's not, and their hue similarity is very low. They're very different in hues. So this would be a relatively non-preferable color palette as a pair. Okay, so what do we do? Well, we'll bring back our target color, and now let us pick a color that is very cool. It's a bluish green, and it is very similar in hue, so it's nearby in hue angle with our target color. So now we've increased aesthetic preference, but what happens to perceptual distance? Well, of course, it's gone down because we've reduced the distance between the colors in color space. So you might say, well, great, now we're increasing perceptual distance and decreasing aesthetic preference and vice versa. Is this an unresolvable conflict? Well, it turns out it's not because we have this third factor. So we've got lightness contrast. So now if we change the lightness of our colors, we can then mitigate this conflict. So now I'm going to just change the lightness of the colors from the pair we just looked at. We're increasing the L star, the lightness of the greenish color, and we're decreasing the lightness of the bluish color. So now we have a higher perceptual distance, and this should lead to higher aesthetic preference. So what this is showing is that conflicts can be resolved, but it's at the cost of constraining candidate colors for a palette. So once we have all of these constraints, we're reducing the number of colors we can choose for a given palette. And of course, this is only two factors we were talking about. We haven't talked about other factors like name difference or semantics. Now, priorities also may vary for different types of visualizations. So for some visualizations, you really might want to prioritize perceptual distance, and that's way more important to you than aesthetics. Whereas for other types of visualizations, you may care more about aesthetics of how people like to look at the visualization as a whole, and you're not concerned as much about discriminating individual colors. So how can we give people the flexibility to navigate these trade-offs on their own, depending on their own priorities for visualization design? This brings us to Cologorical. Cologorical is a color palette generating tool constructed by Connor Gramazio, David Laidlaw, and myself, and we published this work back in 2017. So what does Cologorical do? Well, you tell it the number of colors you want in your palette, and you can control these different sliders to adjust your priorities. These sliders are based on pairwise metrics between each pair of colors within a palette, and they allow you to adjust perceptual distance, name difference, and pair preference. There's also a fourth slider for name uniqueness, but we're not going to talk about that today because we find that it doesn't modulate people's judgments in the tasks that we are interested in. Now, there's a random component to Cologorical, which means that each time you press generate, it will come up with a different palette for you given these slider settings. To evaluate Cologorical, we began by asking whether the slider settings predict behavior, and we did this using two tasks. In the discriminability task, we presented participants with visualizations like this, and their task was to indicate whether there were more unique counties on the left or the right. So to do this task, they had to determine which color corresponded to unique by looking at the legend and figuring out which side of the visualization had more of that color. To assess aesthetics, we showed people the same displays and had them rate how much they liked them on a slider scale from not at all to very much. Okay, let's take a look at some data for these two tasks. To analyze the data, we used multiple linear regression to predict the errors and the preference ratings based on our three factors, so perceptual distance, name difference, and pair preference. And we did this separately for three different palette sizes, 3, 5, or 8 colors. First, we're going to look at the model for errors for 3 color palettes. We explain about 75% of the variance in the errors. with a negative weight on perceptual distance and name difference, and a positive weight on pair preference. So what this means is that people are more likely to make errors if the colors are closer together in color space, if the colors have more similar names, and if people like the pairs within the color combination more. So that points to this trade-off between discriminability and aesthetics that I had mentioned earlier. Now, if we look at 5 and 8 color palettes, we see the same general pattern. Now let's take a look at preference ratings. So for preference ratings for 3 color palettes, we explain almost all of the variance in the data with our 3 factors, with the same weights as what we saw for error. So we find that preferences for the palettes as a whole increase as perceptual distance decreases, name difference decreases, and pairwise preferences increase. So that's the model for 3 colors. If we look at 8 colors, we find the same general pattern, although we're explaining less variance. We see a bit of a different pattern for 5 colors, where we still get a positive weight on pair preference and we get the negative weight on name difference, but we get a positive weight on perceptual distance. This was surprising to us when we saw this, and we were perplexed by it when we published these results. Now I have some ideas of why this might be the case, and I'm happy to talk about that during the questions if you're interested. The next question is, how do categorical palettes compare to other palettes? To address this question, we used the same 2 tasks from before, the discriminability task and the preference task, and the palettes that we used were the following. We used industry standards, so palettes from Color Brewer, Microsoft, and Tableau. We also used randomly generated palettes, but we ensured there was enough distance in color space so that the colors would at least be discriminable. We tested 2 types of categorical palettes, low error palettes and preferable palettes, and these were determined by the data from our first experiment. Here I'm showing 3 color palettes. We also tested 5 color palettes, and we tested 8 color palettes. Now let's look at some data. So here we're going to look at the mean error and mean preference ratings as a function of palette size, separately for our categorical sets and our comparison sets. So let's look at the categorical sets first. For the low error palettes, we see that error increases as palette size increases, expectedly, and we see the same pattern for the preferable palettes, with greater error for 3 color palettes and actually less error for 8 color palettes, and it's not clear why that's the case. But the main thing is to compare these to the comparison sets. And those look like this. So we can see that the categorical palettes are really on par with the comparison sets for error. Now let's look at preference. For preference, the low error palette is relatively neutral on preference, maybe a disliked a bit for 3 color palettes. But the preferable palette is way more preferable, at least for 3 and 8 color palettes. Again, 5 color palettes are a little weird, and again, I can address that during questions if you're interested. Now let's compare this with the comparison sets. Here we see that the comparison sets are about on par with the low error palettes, or even lower, and the categorical preferable palettes are more preferable for 3 and 8 color palettes than the comparison sets. So overall, the categorical palettes are similarly discriminable and can be more preferable than industry standards. So we've talked about Cologorical. Cologorical is a tool for categorical data. Recently, SmartWoo and Szafir have created Color Crafter, which is an automatic generating tool for colors for continuous data. And Color Crafter was created using machine learning algorithms to capture core components of designer color ramps, but it allows you to make your own designer-like color ramps that are not only discriminable, but also similarly aesthetically preferable as the designer color ramps. So the general goal of both of these tools is to provide users with guided flexibility to customize palette design. What do I mean by guided flexibility? Well, users can come up with lots of different options using these tools by manipulating aspects of the sliders or the other filters, but there is guidance within the systems to help create color palettes or color ramps that are effective for visualization. But something is missing from both of these tools. We focus on aspects of perception, naming, and aesthetics, but what we're not taking into account is semantics. And semantics is really important for actually communicating concepts through our visualizations. And semantics is very close to my heart because that's the main focus of my lab's research. So for the remainder of this talk, we're going to talk about issues related to semantics, which are not built into these palette generating tools yet, but there's exciting potential to incorporate them in the future, especially as we learn more about how people infer meaning from colors in visualizations. Okay, so now we're going to talk about semantics for visual communication. When a designer creates a visualization, they have some message that they want to transmit through this visual media. And an observer, when they look at a visualization, they receive a message from this visual medium. There's messages on both sides of this equation, and ideally these messages will be equal. That would be successful visual communication if the observer receives the message that the designer intended to transmit. Now, when observers look at visualizations, they're taking in the information bottom up. So they're looking at the colors, shapes, sizes, and text to be able to figure out what's going on in this visualization. But observers also have expectations about visualizations, and these include expectations about how visual features like color will map onto concepts. And so if we can understand what those expectations are, if we can anticipate those expectations, then designers can use that information to design visualizations that match those expectations, which then hopefully will make the messages on both sides of this equation most likely to be the same. So one of the key questions in my lab is trying to understand the expectations that people have about how visual features will map onto concepts in visualizations. It's easier to interpret encoding systems that match people's expectations. We know this from Lin et al.'s work back in 2013, where they show people graphs where the colors of the bars corresponded to the colors of the things those bars represented. So like bananas is yellow and blueberries is blue. Or they mismatch. So banana is orange and blueberries as green. And they found that it was easier to interpret the graphs where the colors of the bars matched the colors of the things they represented. But expectations are not only limited to cases of resemblance. So they're not only limited to cases where the color in the visualization actually matches or is strongly associated with the concept that that color represents. And sometimes people actually infer concepts are assigned to weakly associated colors rather than strongly associated colors. What do I mean by this? Let's take an example where we've got two colors, a purple and a white, and we have two concepts. And let's say those concepts are trash and paper. And here we're looking at a given case where people are presented with trash, and their task is to figure out which color corresponds with trash. We can represent this situation with a bipartite graph, where we've got two concepts, trash T and paper P, and two colors, purple and white. And the edge thickness represents the association strength between each concept and each color. And just for clarity, we're going to put some numbers next to those edges as well. So one way people might infer which color is assigned to trash will be to only focus on trash because that's the only thing that's relevant at this particular moment. And they compare the association strengths of trash with purple and of trash with white. And in this case, trash is more strongly associated with white than with purple. So that says that trash should go in the white bin. So if you just pick the stronger association, that would be that trash should go with white. But another way to think about this is in the context of the global structure of the encoding system. So remember, we've got two concepts, trash and paper, and we've got two colors, purple and white. And so people could take into account the entire system to figure out which color goes with trash. And to do this, they can solve something like an assignment problem. So to solve an assignment problem here, we would compare the outer edges. So we can sum the weights of the outer edges to see how good that assignment is. And so that gives us 1.1. And we can sum the inner edges, so that's the alternate assignment. And that gives us 0.4. And we can compare them. And then trash would be assigned to the color that is the optimal global assignment. So if we do that, we see that 1.1 is greater than 0.4, which means now trash would go with purple. So remember, that's then opposite of the local solution because trash is more associated with white. But this says trash should go with purple if people are doing something more global. So now let's take a look at what people actually do. So now we're going to look at the mean proportion of times people choose purple or white for trash. Remember, if they're doing it based on just the strongest association, they'll pick white, but if they're doing it based on global assignment, they will pick purple. And that is exactly what we find. So people pick purple even though trash is more strongly associated with white. If we look at the data for paper, not surprisingly, they pick white for paper. So this led us to believe that people use a process called assignment inference when interpreting the meanings of colors in color palettes. So in this process, they estimate the merit of possible assignments, where here merit is determined by association strength, and they determine the assignment that maximizes merit. We can use this information to optimize palette design for interpretability for larger sets of colors. One way to do this is to maximize association strength between each color and the concept to which it's assigned. But an alternative is to maximize association difference. So now each color is not assigned to its strongest associate, but we might be avoiding confusability by reducing association strengths, but maximizing association differences. And we find that this palette on the right is actually easier to interpret. And that's because it's more semantically discriminable. So what do I mean by semantic discriminability? We define this as the ability to infer a unique mapping between visual features and concepts based on visual features and concepts alone. So independent of what actually is encoded in an encoded mapping specified, say, by legends or labels, these are the expectations that people bring when they go to interpret visualizations, regardless of what the encoded mapping specifies. And of course, if the encoded mapping mismatches those expectations, the visualization will be harder to interpret. Now let's return to our discussion of trade-offs. Just as we discussed trade-offs between aesthetics and perceptual discriminability, we can also talk about trade-offs between semantics and perceptual discriminability. Here we're looking at a 2x2 design of different stimuli, where we can vary perceptual discriminability and semantic discriminability independently. Now imagine for each one of these bar graphs, participants are asked to indicate which color indicates mango, or which color indicates watermelon. And there's no legend or label, so they have to use their inferred mapping to complete the task. Well, when semantic discriminability is low, they're nearly at chance regardless of perceptual discriminability. But when semantic discriminability is high, they're very good at the task and similarly good at the task, regardless of whether perceptual discriminability is low or high. Now, of course, for two colors to be semantically discriminable, they must be at least somewhat perceptually discriminable. Otherwise, they could not signal different meanings. But what these results suggest is that when these two factors are in conflict, semantic discriminability actually dominates people's performance for this type of task. And more generally, these results suggest that it can be worth relaxing constraints on perceptual distance when navigating trade-offs for optimal palette design, because relaxing the constraints on perceptual distance broadens the set of potential candidate colors that can be used within a palette when navigating trade-offs with other factors that we mentioned earlier. So far, we've been talking about categorical palettes in our conversation on semantics, but now I want to move to continuous data and talking about color maps. So people have inferences about how colors will map onto quantities in color map visualizations. One of these inferences is the dark is more bias, or people infer that darker colors map to larger quantities. This is the case if you give people a visualization without a legend, they will make that inference. And if you give them visualizations with a legend, they are faster to interpret them when the legend specifies dark is more. So that's the dark is more bias. There's also an opaque is more bias, which is influenced by the background. So the opaque is more bias says that if colors appear to vary in opacity, then dark will mean more on a light background, and light will mean more on a dark background. But critical for this opaque is more bias to operate is that the colors have to appear to vary in opacity. So what do I mean by this? Well, here let's take these medium lightness colors and we're going to put them on a light background and we're going to reduce their opacity. And watch as the colors get lighter and lighter. Okay, now we're going to take those same colors and put them on a dark background, and we're going to reduce their opacity and watch the colors get darker and darker. So the percept of opacity variation is contingent on the ways the colors change as they vary in opacity given the particular background. The background only matters when color maps do appear to vary in opacity. So for the two color scales on the left here, so looking at autumn and hot, these colors are not consistent with opacity variation, which means that the background doesn't matter for those. And it especially matters for grayscale on a white and a black background because that's highly consistent with the colors varying in opacity. So we have to take into account not only the colors in the color scale, but how they relate with the background when determining whether the opaque is more bias is in operation or not. Another question is whether color-based biases like the dark is more bias and the opaque is more bias persist when spatial cues are present to signal more. What do I mean by spatial cues? Well, here we've got color maps where there is a hotspot. And the hotspot might be a cue to larger quantities. As Schott has suggested, surely we tend to assume the center area to be the hottest or coldest, in the same way that we assume the center of a set of concentric rings on a weather map betokens the eye of the storm. So here the question is whether these color-based bias persist in the context of hotspot visualization. So we tested this in a recent experiment, and what we find is that the dark is more bias does persist. And so if we use visualizations like we're looking at here, people's interpretations are uninfluenced by the lightness of the hotspot. People are just faster when dark is more. Now, if we make the hotspot more perceptually pronounced, and we make it a statistically reliable cue to the locus of larger quantities within the context of the visualization seen in a particular sequence, we do find that the lightness of the hotspot has some effect. But still, in cases where the hotspot does represent larger quantities, people are better at interpreting visualizations when the hotspot is dark than when the hotspot is light. So this means that dark more encoding is still easier to interpret. Okay, so in this talk, we've discussed many factors involved in palette design, including perception, naming, aesthetics, affect, and semantics. We've talked about tools that account for perception, naming, and aesthetics, but affect and semantics are not yet built into tools like this. And so that's an exciting direction for future work. And again, our general challenge is how to navigate trade-offs to optimize color palette design for visual communication. There's a lot of really exciting empirical work to be done to figure out how to really navigate these trade-offs effectively. So I'd like to thank members of my lab and my collaborators and my funding sources, and thank you for your attention.
My name is Francesca Samsel, and I'm a research scientist at the Texas Advanced Computing Center at the University of Texas at Austin. I come from a slightly different background. I have decades of experience painting on the sides of buildings and teaching in the art department. I'm going to focus on three areas. And the first principle that I'm going to focus on is that it's the contrast, not the hue itself, but the contrast between the abutting hues that enables you to discriminate between features and see more detail. And the second concept is color interaction. Colors interact, and what abuts one another has a strong influence on how our attention is directed to one and how long our attention sits on one and how prominent the features appear. And the third concept is that the default color maps are very important and they're good for a lot of things, but they're not necessarily good for everything. And it's going to be important just to know what it is that we're sacrificing when we do use them so that you can use them when it's needed and turn elsewhere when that might serve your purposes better. So artistic color theory has been around, I'm going to say 700-800 years, I'm not sure. But this is Jan van Eyck from 1491, and it's a wedding portrait about a couple. It was commissioned by the groom's parents, but here Van Eyck is using color to specifically tell us what this painting is about. The saturated colors are pointing us to the focus of the painting. So the bride's gown is in a saturated, brilliant emerald green, and the bed is in red. Whereas the groom, well, the groom's literally in the shadows. So what that tells us is that the focus is more on the bride, but more specifically, it's on the next generation, because the highest level of attention via color is the bed, and then the next is the bride. So what they're telling us from that use of color is that what we care about in this portrait, or from what his parents care about, is the next generation. And the other thing to note is that there's another principle being used here. If you look at the bride's sleeves in blue and the gold trim, it's kind of surrounding her belly. So that's telling you that that's where the focus is. And then the poor groom here, he literally fades into the background. And there are many symbols around the dog, the shoes, the whatever. And they're also in the background, and they talk about the state of the marriage. They're symbolic from that time, but they are also secondary. So here the artist has used color to direct attention in a hierarchical fashion. The bed's the most important, the bride is next, the groom not so much, the state of the marriage and the holding it together is also important. So the other piece in this puzzle is that there are many color spaces, and the computer is RGB, perceptually interpretable spaces, CRE, LAB, and several others. However, the language of color theory is hue, saturation, and value. So that's what I'm going to be discussing. And yes, hue, saturation, and value is not a perceptually uniform space numerically, but it is a space that enables us to easily adjust the contrast within the color maps just on the fly and without wondering why when I change the blue it looks more green or whatever happens in RGB. Artistic color theory is based on 7 types of contrast. A hue is basic. Is it red? Is it blue? Is it green? What color is it? Value, how light, how dark. Saturation is how intense is the color. So in the middle, you can see 4 bars of intensely saturated colors, and then below it, 4 bars of low saturation, right on just to the left of Antarctica there. And complementary colors, the color bar on the bottom there's warm and cool, and the proportion deals with the volume. I'm going to say the visual volume of color, but we're not going to talk about that so much. And then simultaneity is the principle that fully saturated hues that abut one another have a visual vibration, and that's a really important concept that we're going to go over as it pertains to the rainbow color map. When we're thinking about contrast, what we want to think about is what type of contrast do we need and what level of contrast. It's not about what color do we choose, with the exception of semantic color. And the other principle is that you have a contrast budget. Okay, you can't be spreading the contrast everywhere because then your attention gets distracted. But if you focus the contrast and use only what you need, then there's plenty to direct attention and provide the information to the viewer that you. So here we see the VIS and the traditional cool warm, and then something that we're calling wave color maps because it moves through 3 ranges of luminance. And luminance is the strongest type of contrast we have. And so what I'm pointing out here is the VIS has 1 ramp from dark to light, the cool warm has 2, and the wave color maps have 3. And as you add more luminance ramps, you get more detail. Not always a good thing, sometimes confusing, but just a general principle. Luminance is the strongest form of contrast, the visual contrast that we have. I think it's pretty straightforward. Contrast of hue is simply what color is it? Is it red? Is it green? Is it blue? Is it yellow? And the rainbow and the desaturated rainbow stand on this principle that the detail that you see is via the contrast of hues. And all of the hues are fully saturated. And that's an important point to remember. So here's an example of the desaturated rainbow versus a version of what I call a wave color map, which is similar to the desaturated rainbow, but in a hierarchy of saturation. And so this is what we call a highlight. So the orange on the far right at the top highlights that feature. But if you look at the other features within the data and compare it to what you see in the desaturated rainbow, which is what scientists use when they're looking for detail, I would argue that you see as much on the right as you do on the left. And then there's also this issue of cognitive load. there's a principle called contrast of simultaneity. And that principle is that when you have two hues, or however many hues here, we've got 5 or 6, that are fully saturated and abut one another, there's a very subtle visual vibration between those hues. And it really is, if you try to stare at the desaturated rainbow for quite a while, you can feel the vibration. Whereas on the little right, with the saturation just put in the areas where it's needed, it's a much calmer image. I talk about contrast as being a Goldilocks problem. Okay, if you have too much contrast, as seen on the left in the desaturated rainbow, then it can be pretty cacophonous and hard to concentrate. And so it's a matter of each data set has its own Goldilocks level. It has its own optimal level of contrast. And frankly, that changes as data changes over time. But you can, with several of the tools that we're going to show you in the next half, you can look at different time steps throughout your data and see how a color map is going to look and what you're going to expose across time, not just in a static time step as we've shown here. So on the left you see the cacophony that arises from the desaturated rainbow, although it does provide a lot of detail. And then in the middle, it's I would argue you can see the detail, but it's pretty obscured. And I think it's hard to focus, and it's harder to focus on a Viridis color map when you're trying to track data over time because it is so continuous. And on the right is just one example of an option. And so where we put the contrast on an area that's of importance and that they want to track over time. This is combustion data from Lawrence Livermore. So the next topic is interaction of color. Colors that abut one another have an influence on each other. And even the colors surrounding one another have an influence on each other. And in painting, you can control this because you control what goes next to what. But in scientific visualization, the data dictates that, and especially time-varying data, this becomes a problem. So it's important to choose hues that are harmonious and that will work well together regardless of their distribution. One way to address this is to increase your use of neutrals or low saturated hues. This will calm everything down. Here is a painting on the right where the color swatches in the middle are drawn from that painting. And there's not too much else in the way of, kind of hue ranges and whatnot going on other than the swatches that I've pulled out. And you can see that even though they're kind of rough brushstrokes and whatnot, you have a total sense of what's going on in this palette of totally muted hues. So it's a bit like a symphony. If you've got the trombones and the steel drums or the bass or whatever playing in the background, and you've got a delicate piccolo in trying to be heard, it simply isn't going to be heard. And so the same is true with color. That if you've got a lot of saturation across your VIS, then you're going to have a hard time either adding anything if you need to add any other like contour lines or other elements, especially if it's a multivariate color set. But if you use your neutrals, then you'll have an easier time. So when we begin to talk about color interaction, I think it's important to take a pause and look at some specifics of what that means. So what we're looking at right now is a visualization of different types of vegetation in the northern part of the Alaska tundra. And so what Ari's done here is used really what is a pretty analogous palette. So we paid attention to analogous colors often play nicely together and produce a common result. But he has used some pretty high saturations, not across the board, but in the lower areas. And so you say, well, okay, I can distinguish. And that's true, you can distinguish between them. But I would say that there is a cost. And that cost is often not fully accounted for. So I would have a hard time living in this room And so if you're spending a lot of time with your data and looking through a lot of different slices of this or versions of that, you're spending time in a room like this, and it will take its toll. There's a reason why the Marriott designs rooms like this. And it's because they just provide a peaceful, calmer environment. But it isn't that this palette is without contrast. It simply is that the volume of the contrast is lower. And so all of the hues that are pulled all of the hues that you see in this middle section are pulled from the palette within the room, which is very carefully designed. And so I would say it's the same analogy with the symphony. If you've got a quiet piccolo, it can be heard unless you have all of the drums playing. And then this is an example, Galen Gisler was studying asteroid impacts water in the ocean, actually. And on the upper left is a visualization that this is what he had and he brought to us, and it's something called rho, and it's a combination of the variables that they look at. It's a mathematical formula that combines the temperature, the pressure, and the water vapor so that you can kind of see those three items. And you can see those three items in the upper left. But the problem is that that you can't really see those hues in three dimensions because the rainbow color map does not do well for volume rendering, especially if you start to use the opacity functions, because the hues in that color map don't layer well. So here you can see we switched to one of these wave color maps, and the goal was to be able to see the structures within the impact, and this is the temperature, but it also indicates where the pressure is. And you can clearly see the structures, that the red at the high end of the temperature and the blue at the low end. And by controlling for opacity, that's what enables us to make some kind of, the blue is more ghost-like and the red is more solid. So when you're thinking about volume rendering, it's really important to consider how the hues are going to interact with one another as they are stacked. For that reason, this is the color map that I always begin with if I'm working on a volume rendering data set that needs to be volume rendered, because it's a very clear addition of color one on top of the other, and it doesn't get in the way of seeing the structures. This can be found on our website, cybersecurity.org. This is another example of a cool, warm, kind of a color setup. It's an obvious one, as it's water and temperature, so the semantics work out with the blue and red ranges. And because it's volume rendering, you can see I've used also the ramps that are analogous in hue, so that when the hues stack on top of each other, they retain their blue or their red-orange range, rather than becoming mud. Like if you had a red and a green, they would overlap one another and they would turn to brown. So this is a set of scientists who were modeling supernovas, seeking to track the origins of the first water in the universe. And it obviously depends a lot on opacity, but it's two variables within one volumetric rendering. So before we get into the next topic of interaction, I wanted to pause for a second and talk about data ranges, because obviously the right data range and being able to focus your contrast within that data range is critical. And so here you see an example of a data set where there's a histogram. You see the image in a histogram, and that system comes from color moves, which is we'll show you again in the next session. But on the far upper left, you'll see just a red, yellow, white color map that covers the entire data range. And if you go on the top right, you will see one where that same color map covers 1% of the data, okay? Just 1% of the data. But when we talked to the scientists, what they were really interested in, and the one that worked for them best, was the middle bottom. And that, if you look, it goes from 42.9 to 44.4. And if you're working in traditional visualization tools, honing in on a range that specific is pretty time consuming. So I would encourage folks to think about this kind of interactive color situation where you can see the colors change on your data as you're sliding the controls back and forth. And that really, if you know what features you're looking for, it enables you to identify that data range clearly. Also enables you to sort of experiment and see what other features you might find. So turning to some real practical examples, I'm starting with the concept that less is more. So this visualization across the top was brought to me, and I said, oh, this is interesting. Okay, what is it that you're looking to see? And I was told, well, we need to see the black line. And my first question, I had to squint a little and said, oh, I see that black line. And I said, and tell me what else? Well, we want to see how much of the black line, how much of the area of the square that the black line crosses is outside the circle and inside the circle, and how much is and how close is it to being a complete circle versus not, as is on the left. And I said, oh, okay, so what about the red? Well, that area is not important. I said, well, what about the dark blue? Well, that area is not important either. So the first thing I do is I say, okay, we're going to take away the saturation from the areas that aren't important. And so the image below, what we did is less is more. So we took away the saturation where it wasn't needed. Luminance is the strongest kind of contrast. And because the black line was thin, we needed some pretty solid contrast. But they also wanted to direct attention to the squares that were relevant. And so those you can see have a yellow tint in them, whereas the background is gray and the middle is a very light gray. And then they wanted to be able to distinguish between the three regions of those kind of yellow-gray squares. So there are three different yellows, varying from kind of a light saturated to a gray muted yellow. And so all of a sudden you can see the black line, and you're not struggling to have your attention be pulled away by the saturated hues in the visualization. So I thought that one was pretty successful. So that was a pretty basic color problem. But once you get into multivariate and three-dimensional viz, obviously it gets a little more complicated. So what I'm going to do is show you a few examples of color theory applied to those types of problems. So even when the visualization is more complicated and there are a number of variables and dimensions and whatnot, the same principles apply. So this is a visualization of 4 different water masses underneath the Antarctic ice sheet, the Ronnie Filchner ice shelves, actually. And so these scientists were interested in seeing how the water masses, which are on the temperature or salinity scale, different ratios and relationships, how they move over time. And so we needed to color the samples, but we also needed the streamlines to show the flow. So this is a basic cool warm split up, just using the cool blue, green, and turquoise to represent one set of the water masses. The warm yellow and orange represents the flow, and then we stuck with just a blue for the bathymetry at the bottom. I'm going to close with 2 items. The first is a series of clips from a video we did a few years ago on asteroid impacts, and it was an ensemble set of visualizations by Gale and Gisler. They were looking at what size asteroid and what characteristics of asteroid could cause a tsunami threat. And this clip has several different techniques that were covered earlier, but also some examples of other ideas.
Okay, I know that was a lot of material, so thank you for sitting through all that. But Karen and I are here. A lot of material, so thank you for sitting through all that. But Karen and I are here. A lot of material. Okay, sorry about that. Is that better? So what we talked about were three very different perspectives on color for visualization, and you can see we all come from different communities. But I've been working on color for about 7 years with the folks at Los Alamos, and what we've really found is that we need the voices and expertise from different areas to really find effective solutions. So that's why Danielle and Karen and I have come together and to try and find where the crossovers go and how we might improve the effectiveness of each other's research and find solution, kind of holistic solutions. So we're happy to answer questions unless we've worn you out already. And if you could monitor the questions, I don't know who's in the technical space because I'm having a hard time. Okay, so what we have coming up in the second half, so that you know, is, that was all our talking. And but in the second half, it's totally hands-on. And we're going to start with Karen and Danielle have organized a workbook for you so you can try out their tools on actual data, and that should be pretty fun. And then we're going to dive into, I'll show you about color moves, which you saw a few images and the results of in first half there from my talk a little bit. And then we're going to learn about CCC tool, which is an incredible piece of work by Pascal Nardini, who but is probably the most complex of the tools for custom color map creation, quite interesting. And then Pascal and I both will have breakout rooms and your ability to come work with actual data. We both have set up tutorials so that you can work online. So join us for the second half after the break. Okay.
Ecosystems are complex and dynamic. To investigate the dynamic nature of ecosystems, we have developed a prototype of a visual analytics system based on empirical dynamic modeling, EDM. EDM is a set of analytical methods rooted in nonlinear state space reconstruction. Integrating EDM with dimensionality reduction, brush-linked visualizations, and visual summarization support understandings of ecosystem dynamics.
Visualizing streaming of big data may be difficult if the visual idiom gets cluttered. Although some techniques solve this issue by aggregating data into different idioms, each representing a different period, they still lack transitions to help people understand how data points get from one visual idiom to another. To solve this issue, we proposed several transitions between several pairs of visualizations. We tested them through a user study where participants watched a video per transition and had to answer 7 questions.
Was actually responding to someone else's question, asking about color categories, or does language influence color perception? So, so thank you, Maureen, for answering some of those questions. Historically, basically in the work in the 70s and even before that in cognition and in linguistics suggested that language may not actually influence color perception. And then more recently, work has been suggesting that it actually might. And so Maureen was referencing a study looking at participants who speak Russian, where there's 2 different terms for light blue and dark blue, whereas in English, we just have blue, so we don't have different terms for those. And so evidence suggests that people who do have different terms for these 2 different categories have greater discriminability. So if you were asking me to discriminate between a light blue and a dark blue, I wouldn't be as good at that as someone who is fluent in Russian, who has those different color categories. And so, like I said, this has been a controversial topic, but more and more evidence is suggesting that language may actually shape color perception in ways that we didn't think before.
Yeah, and I think there are many things that shape color perception because I think, and we all have different levels of discriminability. I mean, just inherently. So it's really an interesting topic. It's more complex than just a single answer. I see someone else coming in. I don't know if that's with a question. If not. So I see, how does it compare with the example, just simply being more practical at color evaluation? So do you see that one, Karen? This is from Maureen Stone. One question is the strength to the effect. How does it compare, for example, to simply being more practiced at color evaluation? Well, I think that is, we often find we don't let people do our studies more than twice because they get better.
I think Maria is still referring to the language effect. So it's possible that someone who is a native Russian speaker who has different terms for light blue and dark blue might by default be better at discriminating those colors than someone who is, say, an English speaker who doesn't have two terms for that. But if the English speaker is highly trained in color discriminability, then they might be as good as, or if not better than the native Russian speaker. I'm pretty sure that's what Maria was referring to there as part of that conversation. Yeah.
Okay, well, we have a very packed second part coming up. So stretch a bit, take a walk, and we are going to be doing the fun part in a second. So come back, we'll see you then, okay?
Ecosystems are complex and dynamic. To investigate the dynamic nature of ecosystems, we have developed a prototype of a visual analytics system based on empirical dynamic modeling, EDM. EDM is a set of analytical methods rooted in nonlinear state space reconstruction. Integrating EDM with dimensionality reduction, brush-linked visualizations, and visual summarization support understandings of ecosystem dynamics.
Visualizing streaming of big data may be difficult if the visual idiom gets cluttered. Although some techniques solve this issue by aggregating data into different idioms, each representing a different period, they still lack transitions to help people understand how data points get from one visual idiom to another. To solve this issue, we proposed several transitions between several pairs of visualizations. We tested them through a user study where participants watched a video per transition and had to answer 7 questions.
As commonly known, dimensionality reduction techniques and their interpretations are complex, biased, and uncertain. In drug design, this highly complicates the search for similar and new chemical compounds. To overcome this issue, Canva brings comparison of different molecular descriptors and properties into one tool, featuring planar, 3D, and table views for evaluating the trustworthiness of high-dimensional data projection.
We propose X-matrix, a novel method for random forest interpretability. From a random forest model, a logic rule is extracted from each decision path on every decision tree. Once the complete set of logic rules is obtained, visual representations can be built for global and local explanations. X-matrix, making random forests interpretable.
Data videos are quite popular nowadays. They usually show changes in the data. However, creating a data video requires multiple skills, and the process is usually laborious and iterative. Our approach focuses on automatic and interactive visual enhancement of important changes in time series data with data video.
How do we represent remote users in synchronized visualizations while supporting divergent exploration? We present cursors, the basic unit of user representation in a collaborative visualization. They can vary significantly in appearance, as you can see. Cursors enable collaborative interaction techniques, such as peeking, tracking, and forking. To learn more, please read our paper representing real-time multi-user collaboration and visualization.
The success of a convolutional neural network has been attracting many students and practitioners to learn the exciting technology. However, for beginners, the thinking model is not easy to understand. We introduced the Explainer, an interactive visualization tool to help beginners more easily learn about convolutional neural network. Using the Explainer, users can progressively explore the thinking model with real-life images in their browser, getting a comprehensive understanding of both high-level model structure and low-level underlying mathematical operations.
We have seen many visualizations for tree data structures, but when showing changes in trees over time, some focus on displaying hierarchy, while others highlight their changes. With split streams, we combine two approaches and their individual benefits. We evaluated our method in a user study and consider it a general-purpose method for the visualization of dynamic hierarchies. Our JavaScript library is openly available.
CMed is a visual analytics framework for exploring medical image data annotations acquired from crowdsourcing. CMed can be used to visualize, classify, and filter crowdsourced clinical data based on a number of different metrics such as detection rate, logged events, and clustering of the annotations. CMed provides several interactive linked visualization components to analyze the crowd annotation results for a particular video and the associated workers.
Drjs is a JavaScript library for dimensionality reduction where we implemented 11 DR methods. A typical use case for Drjs is a web tool using DR. You just need to import Drjs, create a DR object, and then call the transfer method. That's it. See the talk, the paper, or the supplemental material for more information.
Magnetic reconnection is a ubiquitous and complex physical process that occurs throughout the universe. Locally, this process is observed when the solar wind interacts with the Earth's magnetosphere, causing magnetic field lines to break and reconnect. One of the results of this process can be seen from Earth as the aurorae. In our talk, we introduce scalar field topology as a method to identify and analyze features in 2D magnetic reconnection simulations.
Transitions are widely used in data videos to build seamless changes between video narrative. As the attention cue, they can not only keep viewers oriented but also express narrative information. After conducting a content analysis on the transitions in the dataset, we provide a comprehensive taxonomy of narrative transitions in data videos.
This is a picture of a Tableau visualization within the browser. The data behind the visualization does not exist here, and Tableau is not running. This is just an image. However, parts of this image are fully interactive. Please join our presentation to see how we can share interactive visualizations across the web, free from any dependency on data or visualization application.
Testing environment for continuous color maps. Many other fields in the computer science do it, we should do it too. With our work, we introduced the approach of using test functions as a standard evaluation method. We present a test suite for continuous color maps implemented in the CCC tool. Adapt the task to your requirements at the interactive testing section and observe them at the testing evaluation section.
Information about vulnerabilities helps defenders prioritize what they need to patch, but this information can be difficult to interpret. In this paper, we support interpretability using a focus and context approach to visualizing vulnerability data, including a clustering overview, plots that enable filtering based on severity, and explanations of text features and descriptions. We invite you to read our paper to learn more.
We present the first generic design space and library for visual piling. Inspired by physically piling paper documents, visual piling describes an interface for spatial organization of visual artifacts into piles of partially overlapping items. Piling affords interactive grouping, arrangement, previewing, browsing, and aggregation to reduce the complexity and support comparison of large collections of small multiples.
Hello. Student competition is intrinsic to the pedagogy of cybersecurity education. At RIT, we have observed that the collegiate penetration testing competition and other related competitions are missing a key element: visualization. In this position paper, we provide an architecture and plan to create compelling experiences for participants and spectators. In doing so, we can potentially attract new talent into the field.
Ray tracing techniques can create images of astonishing realism and beauty. In the last years, the performance of those techniques has been increased significantly using dedicated hardware. Who thought that it's also possible to accelerate this? We show how to dramatically accelerate force-directed graph drawing with RT cores, yielding a speed up of 4 to 13x. If you want to know more, please see our talk.
Programmers often make mistakes like this. A VIS function is incorrectly called with a string. A programming language can catch such mistakes early on, but for this, it needs a type system. We present Typical, an interactive visualization tool for programming language designers. Typical allows them to explore common function type signatures and helps create a type system.
Asteroids have always been and will always be a threat to life on Earth. Most likely, an asteroid will hit deep water, but what properties will actually lead to a threat like a tsunami? Ensemble simulations are a common tool to understand the effect of different parameters like the size of the asteroid. We propose an interactive visual approach to help analyzing deepwater asteroid impact simulation ensembles.
Deep learning models have become ubiquitous, but we often lack interpretations for their decisions. We developed a visual analytics system to interpret models that perform multi-class DGA classification. For each layer of the model, we visualize clusters inside its activation data, showing how classes and clusters relate to each other. In addition, we provide a decision tree to explain how these clusters are constructed.
We asked participants to recreate bar graphs. When the bar was alone, we saw a different pattern of error than when the bar was presented with context in a stacked bar graph. We found that absolute error increased for higher bars when they were presented alone. We also found that there was a bias in the responses such that they were repulsed from an implicit 50% mark. We found a magic number, 10%, to predict error. Participants are usually within 10% of the height of the bar.
Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster.
Connect to the data you care about. Sort, highlight, drill down, or filter your data in seconds. Add calculations to extend your data. With Tableau, you can keep on asking questions in the data until you discover the root cause. Tableau. Answer questions at the speed of thought.
We present a flexible and easy-to-use software infrastructure for interactive rendering of large-scale display walls, either from on-site or from remote cluster. The display servers can easily be configured to support a range of typical network and display hardware configurations. The client library provides a straightforward interface for easy integration into CPU and GPU renderers. We also demonstrate this framework for use in deploying low-cost alternatives for display walls.
After determining the departure timestamp, the experts then moved to verify the recommended shuttle stops and routes. Note that Shuttle VIS recommends the default shuttle stops and routes based on the metric of average distance. Then they observed that in our cluster 4, the system recommends Hejiangjinyuan as the shuttle bus stop, but the experts identified that another drop-off spot Panshanhuiyuan is located in the middle part in this regional cluster.
Predictions made by machine learning models can be hard to understand. Counterfactual explanations explain model predictions by telling the users how to obtain the desired prediction with minimal changes to the input. We introduce Drjs, an interactive visualization system that supports counterfactual-based explorations on individual instances and data subgroups. Please check our paper for more details.
In this paper, we investigate design choices for Choropleth maps by domain experts. We tackle 2 research questions: how do domain tasks influence the design choices, and what equal error projection is preferred. Through a survey, we collected 40 Choropleth maps designed by 20 social scientists, and our analysis suggests that the choices vary across tasks, the projection was most important, and the equal error projection was preferred.
VIS is a visual support system for the development of visualization algorithms. It has live compilation, automatic version control, predefined interactions, and tools for visual parameter analysis. By displaying the complete history of the algorithm, users get insights into the correlation between source code changes and visual differences.
Interacting with large datasets could be painfully slow. We can reduce the latency with faster backends, but that's not always attainable. Here, we investigate a solution that only leverages techniques on the front end. We propose interaction snapshots, where users can view the results at a later time. We found that users experienced much less frustration and were able to complete the tasks faster.
DVR has always been from considerable interest to the scientific community. To this day, traditional desktop setups are the gold standard. However, what if we could utilize DVR in virtual reality? Now you think, VR and DVR are so computationally expensive, how is this even feasible? Come to my talk and we present you a straightforward solution to visualize volumetric datasets with high refresh rates on VR devices.
Imagine you have tons of text data to analyze. And you want to get an overview of your data, but traditional topping modeling techniques such as LDA are not working for you. Then, why don't you try Architect? We introduced a scalable and flexible way to interactively build hierarchical topics.
A Morse-Mean complex is a topological descriptor that captures the gradient flow of a scalar function. The best-known approaches for its computation incur large runtimes for bigger datasets. We address this gap by introducing the first completely GPU parallel pipeline, which achieves speedups of up to 7x, with our individual algorithms attaining speedups of up to 129x and 4.5x.
In this talk, we introduce CallFlow, an interactive visual analysis tool that provides a high-level overview of performance profiles from large-scale scientific applications. CallFlow visualizes the flow of resource of a program execution as a Sankey diagram to detect performance bottlenecks in parallel codes. CallFlow simplifies these calling context trees based on semantic information by constructing supergraphs.
How do you visualize the nanoscale, 1/1000th of a meter, for the public? As part of a Science Center exhibition, we developed an immersive environment that explains nanoconcepts by allowing users to explore nanoproperties. We reflect on how exploration, the confluence of explanatory and exploratory visualization, can be applied to visualization in public spaces.
When developing a deep learning model, people typically struggle to optimize hyperparameters that affecting the model performance. To relieve the pain of this manual trial process, AutoML has been developed as a solution. However, to maximize the potential of the AutoML, people should identify a good AutoML setting for their task. Hypertender helps to maximize the potential by visualizing AutoML algorithm behavior and guiding effective hyperparameters.
Evaluating alternative interpretations is an essential part of complex sense-making, but the resulting ambiguity is rarely considered in the design of visual analytic systems. Avalanche forecasters rely on sparse and human-produced data to assess avalanche hazards, often resulting in ambiguous interpretations. We used simple glyphs and unit visualizations to specifically consider and support ambiguity in the avalanche forecaster's sense-making processes.
Scatter plots and parallel coordinates are widely used for visualizing multivariate discrete data. However, for multivariate continuous data, the continuous scatter plots and continuous parallel coordinates are more suitable. In this work, we extend them to uncertain data. Additionally, we also extend fibers to uncertain data. If you are interested, come to our presentation.
Pixel Clipper allows visitors to quickly and expressively extract visual clippings from visualizations and add comments to them. The clippings are useful for engaging the public with complex datasets because they are entry points into the visualization. This can be applied in a wide range of engagement experiences, such as the use of facilitated and ambient displays at public engagement events.
While meetings are an essential part of everyday business life, most calendar visualizations are not designed for retrospection. We present a tool consisting of 4 coordinated views that integrate into the user's daily workflow and are designed to promote self-awareness about past scheduling decisions. We discuss the insights gained from an internal user study and from a field deployment. We also discuss how we strongly inherit from the principles of personal visual analytics despite targeting a professional environment.
We present a method for real-time ray tracing of stream tubes for fluid flows and diffusion tensor MRI. Rays are traced through a sparse voxel lock tree until they intersect leaf nodes which contain tube segments. This checkerboard pattern indicates voxel boundaries. Within leaf nodes, we can ray trace straight tube segments or ray cast curved tube segments.
In this study, we designed a system named Causality Explorer to facilitate the causal analysis. Users can explore the causal graph to perceive the causality and its uncertainty. validate the causality with the raw data, and apply the confirmed causality to what-if analysis.
Forensic investigation of file system metadata is a difficult and time-consuming task that requires deep expert knowledge. Following a user-centered design, we implemented an analytical tool to guide analysts during a security incident investigation. The evaluation proved that the tool could significantly improve the efficiency of disk exploration, even for less experienced analysts.
Analyzing urban heat island phenomena, which cause higher temperature in cities, requires to explore the relationships between climate and urban morphology. In an ongoing co-visualization framework, we propose different ways to visually explore both urban and climate data at a city block scale in order to support the analysis of urban heat islands.
Yeah, so maybe you could also explain the breakout rooms when we get a little closer.
Sounds good. So I think Karen and I are not planning on doing a breakout room, just kind of keeping everybody here for simplicity. Since our tools are very like beginner focused, I don't think it'll take much time.
Oh, well, that makes sense. I never considered that.
Awesome. Thank you so much and welcome everybody. So thanks for joining us here for the more hands-on portion of this color tutorial. We're going to be going through a series of tools that we've all collectively developed over time. And we're going to talk a little bit about the theory behind the tool, how does it work, that kind of thing, and then move from there into a little bit of hands-on play. So this first half here will be Karen and I talking a little bit about two tools that we built that are focused more on bootstrapping preliminary color encoding design. So those tools are Color Crafter and Cologorical. So I'm going to, if you bear with me a minute, kick up a quick presentation that helps describe some of the background behind Color Crafter. Uh-oh, did I freeze? Do you see? No, you probably don't see PowerPoint. All right, do we see PowerPoint now? Yes, perfect. All right, sorry, my computer has issues sometimes. So if I totally freeze, I will hard reset and be right back. But so Color Crafter is a product from an algorithm that Steve Smart, Kiki Wu, and I published last year at VIS. And the basic idea is that we want to help people automate how to build high quality color ramps. So I'm going to go over right now a little bit of the theory and motivation, and then we'll do a quick demo. And then when we get into the breakouts, I'll show you a little bit more about the functionality of the tool itself. So with Color Crafter, a lot of our motivation came from the fact that if you look at visualization systems, so this is a snapshot of tools published at VAST in 2018, you'll start to notice maybe a common theme. And that's that they all look very similar, right? They've all got a similar color scheme. And what we found is that just from a quick skim, 25% of VAST papers that year contained at least one instance of a red-blue color map. So for some folks, you're good with that. We know red-blue works. We're comfortable with it. We'd rather have something that works and not worry about the creative agency that comes along with it. Perfectly valid perspective. But if we think about things like marketing strategies where we have specific colors that we might need to design for, last time that I checked, Color Brewer doesn't really have a lift pink ramp. So the question becomes, how do we actually think about designing for color encodings in cases where we want to have this kind of more rich, more specific, more varied application of color? And so to do that, if we take this idea of, if we take this idea of our Skype blue, for example, let's just start there. What we can do is we can actually think about what are all of the possible paths that could traverse that Skype blue to create a robust and effective color encoding. And that's essentially what we're trying to do with color crafting. Getting it mixed up already. That's essentially what we're trying to do with color crafting is we're trying to figure out how exactly do we support people in rapidly and effectively creating color encodings for continuous data that leverage known and desired colors. So I'm just going to talk a little bit, since I've only got a few minutes, about the background for the tool, general motivation, the algorithm we designed, and then if there's time permitting, I'll do a quick demo. Otherwise, we'll push that to the breakout session. But just to get us started on the background, I want to establish some common terminology. So one of the fun things that came for us out of putting together this tutorial is we realized there is huge variance in the way that we all talk about color encoding design. And we could be talking about two different things using the same words and talking past each other. And so what I want to do is I just want to establish, for the purposes of what I'm talking about here, when I'm talking about color ramps, I'm talking about quantitative and ordinal data, right? This is kind of your continuous color encoding. When I'm talking about color palettes, there I'm talking about categorical data. And I only bring that up for clarity in the division because that's pretty much the last time I'm going to talk about color palettes right now. So when we're thinking about tools for generating color ramps, we have this dichotomy between the fully designer, we have lots of fabulous looking designs. You just choose your favorite of the set that's been provided to you. So this is the color brewer approach. And then the flip side of that is the fully manual, thinking about how can I support people in guiding effective color choices. So Color Picker for Data is one of these that does interpolation in HCL. And if we look at these two different endpoints, one of the tricks when it comes to effectively using these kinds of tools is figuring out how do we actually work with them effectively? How do we help people very quickly be able to have agency in the kinds of things that they build, like with Color Picker for Data, while also retaining the desirable aesthetic properties that we get out of something like Color Brewer? And so one thing you could think about is, well, maybe we just need to find the right endpoints and interpolate between them. And you can see an example here where the top ramp is our Color Brewer greens. The bottom ramp is an LCH interpolation of the same endpoints of the data. And what you can see is that that top ramp is a whole lot better from an aesthetic perspective than the bottom one. And this just is one example of how color ramps are not as good as the quality of their endpoints. Well, one of the things that you might be picking up on from a lot of the discussions this morning, though, is that building things like these hand-designed ramps is really, really hard. So Roxana Bujak et al. Had a great paper back in 2017 where they summarized best practices for color encodings. But if I get rid of those practices that are really hard to implement at design time, and then I get rid of those practices that don't require extensive knowledge of color science, I pretty much end up with one driving principle. So what we're trying to do in color crafting is trying to empower people to leverage effective best practices by not necessarily taking this heuristic approach where we have to manually implement all of these different guidelines and designs, but rather by taking more of a data-driven approach. And the fundamental idea that you will see when you're working with Color Crafter is that it is based on this idea that we can represent a color encoding as a path through three-dimensional color space. So here, for example, we have one of our color brewer ramps on the top, and we can see this path that that ramp traverses in hue space through the A-B plane on the left, and the lightness chroma path that it traces on the right. And one of the things I want to call your attention to here is that these curves are not straight line interpolations. So that's the second piece that's going to come into play in just a second here. So if we take this data-driven approach, Color Crafter uses these curve structures and this fundamental observation that ramps really are curves, that they really are three-dimensional geographic paths through a perceptual space to try to drive effective color encoding design. And rather than going to designers and having them enumerate best practices, what we're trying to do is figure out, can we provide a scaffolding that reflects best practices that then the designer can use to refine their encoding? And so the way we do this is through an algorithm that traverses in 3 steps. I'm just going to cover this at the very high level 10,000 foot view. If you want more details, they're either in the paper or I'm happy to chat during the breakout. But the basic idea is we cluster a set of curves that reflect handcrafted design practices. We model those clusters to try to find characteristic patterns these paths take. And then we seed those paths on our desired colors to actually generate our encoding. And so if we look at this, the way that Color Crafter actually has generated these paths is we started with a collection of 222 handcrafted ramps that were collected from a variety of sources, including Color Brewer, Tableau, R, and Color Lovers. And once we created this corpus, we normalized our curves to a set of 9 values interpolated in CIE lab space. And then we did an arc length interpolation to renormalize the perceptual distance steps between any pair of adjacent colors. So this is why Color Crafter, you'll see, has 9 step ramps that it's generating. Once we were able to create these curves, we clustered them together using a k-means clustering algorithm. And we tried to figure out, all right, what are the structures that reflect common patterns that we see across our corpus? And so these characteristic curves reflect the 9 different selections that you will see in Color Crafter. After we have these characteristic curves, what we want to try and do is bind them to our target color and color space. So the way that we do this is by minimizing the distance between our lightness of our desired color and our lightness structure that's reflected in our characteristic curve. As was talked about in the earlier discussions, lightness, luminance is one of the most important elements of a continuous encoding design. So we wanted to try and prioritize that in the ways that we're creating these encodings. So essentially what we do is if we have our curve, we find in an L star space the point in that curve that is closest to our seed color. we translate the curve such that those lightness values align, and then we rotate the curve such that it mirrors up with that particular value in color space to get our desired seeding color. And I'm not going to jump into the details of the evaluation, but just a TLDR as to why we use this approach is that in general, these kinds of curves, despite their nonlinearities, are actually more accurate for estimating individual values than a linearly interpolated ramp. And we found they were comparable to designer ramps. And we found that people actually in professional designers in experimental evaluation found our approach more aesthetically pleasing than linear ramps and comparable to and trending towards more aesthetically pleasing than designer ramps. So what you will see when we do the walkthrough here in a minute is how these principles and practices manifest in the design of this tool. And just to give you a quick preview for folks looking for the link, and I'll drop these links in the Zoom chat because I want to make sure that Karen has time to give her intro for Cologorical. But the current alpha version of the deployments, note that the interface is still in development, so it might be a little buggy, so let me know when inevitably things break. But the current interface deployment for this tool is at cuvisuallab.org/colorcrafter. And when we get to the hands-out on breakout rooms, we'll have a series of structured activities where we will play with Colorcrafter and Cologorical directly in an observable notebook. So if you want to link to that notebook, that link is here. And again, I will drop it in the chats. I think for the interest of time, Karen, I will go ahead and hand it off to you for Cologorical, and then I'll do the quick walkthrough of color crafting features as part of our hands-on session.
Sounds good. Okay, and I'm going to do kind of the opposite, which is a couple slides, and then do the walkthrough in here. So I'm going to share my screen just for a moment to do that. Okay, as I talked about introducing Cologorical during my talk earlier, but hopefully all of you were at. So I'm just going to just show you the interface again here, and then we're going to zip into the actual web browser so I can click around and show you some things. So this is a screenshot of Cologorical, and it has these sliders, which allows you to adjust the prioritization you have on perceptual distance, name difference, and pair preference. Also, name uniqueness is a slider, but we don't worry about that one because we found in our evaluations that did not modulate people's behavior. But if you want to play with that one, go ahead and explore that as well. So in creating Cologorical, we started with a set of seed colors that were, based on previous work, found to be aesthetically preferable, so seed individual colors. And then we designed the palettes based on pairwise judgments around those seed colors. So perceptual distance is delta E 2000, and name difference is based on Huron Stone's work, and pair preference is based on work by myself and Steve Palmer back in 2011. And so then you can tell the number of colors that you want and adjust the sliders and then have it create palettes for you. Now, I mentioned during the talk, we evaluated these palettes by comparing them with industry standards, random and 2 types of Cologorical palettes for 3, 5, and 8 color palettes. And if we just look at those data again for a sec, so I want to call your attention to this 3 and 5 color palettes being really preferable, sorry, 3 and 8 and 5 being low. And this, as I mentioned during my talk earlier, was really confusing for us. I have a hypothesis now of why this is the case, and I just want to draw this to your attention because one of the palette sizes we're going to be exploring in the hands-on component is 5 color palettes. So I'm going to tell you why I think this is happening so you can play with it on your own. Okay, so what's the issue with 5 color palettes? Here we've got our hue circle. And remember that aesthetic preference, so pair preferences, and this is empirically based, is based on hue similarity, coolness, and lightness contrast. And we're going to ignore lightness contrast for a moment because we're in a L-star plane. So let's say we start with this target color here, and we want to have hue similarity and coolness. So we might pick this color 2 over here. And then maybe we pick this color 3 over here because we're keeping hue similarity, the colors are close together, and they're cool. If we were going to stay in this part of the color space and go more towards purple, we would lose coolness. So that means we're going to go more towards green. And so we get another color here, and then we might get up here. Now, we are keeping hue similarity low. All the colors are close together. We're trying to keep them cool. But the problem is this color here is one of the most least disliked colors. And this is data from the US. These are just average color preferences. And this is the most disliked color. There are cross-cultural differences in color preferences, but that tends to be the case across lots of different cultures that we have looked at. And so why is that the case? I'm not going to go too much into theory right now. I just want to introduce the idea of the ecological valence theory. And the idea is that people like colors that remind them of things they like, and they dislike colors that remind them of things they dislike. So on average, that dark yellowish color is negative. There are positive things that are dark yellow, like cornbread, but it also is the color of sewage and rotting food and mold and vomit, and I spared you the picture of that. And so we had entertained the idea of actually just carving out that part of color space when creating Cologorical. We didn't want to carve out any parts of color space. So this can happen. And so I think once you get to 8 colors, you're just gonna end up getting further apart in the space. So you're not gonna land in that part of the space. So I think that is what's going on. And so the solution to this you can use our hue filters. So you can actually filter out that part of the space, and I'll show you how to do that. So if you don't want to allow Cologorical to go there, you can just tell it not to. Okay, so let us now take a look at Cologorical. And can you give me like a hand of how many minutes I have?
However many you need. I think we're going to run straight from this into the breakout session. So if you need a little extra time, just go for it.
I will be fast here. So what we're going to do, so here's Cologorical, welcome. So we're going to tell it the number of colors to use. So I'm going to say 3. I have pair preference ramped all the way up, and I'm going to tell it to generate. And it will generate a palette with 3 colors, and it gives us this one. Notice the colors are similar in hue and they are cool. And each time I press generate, it's going to give us a different set of colors. And so what this means is that if it gives you a set that you're not so into, you can just generate and you can pick new ones. If you have ones that you like but you want to see more and you want some to go away, say I don't like this because it's too green, I can just exit it out and it'll go away. I can also minimize these, and so then we see the little parts of the palettes, but they're not taking up the whole screen. So that's with pair preference all the way maxed out. And now I'm going to make that go low and perceptual distance go high. And we can see what that does. So now aesthetically, at least based on our models, this would not be that preferable, but the colors are more discriminable. And then similarly with name difference, then it allows you to get colors that should be more easily named by different colors. Now, Cologorical has a stochastic component. There's a random component, and the palette is, we score them so it's only as good as the worst pair within it. But this is not meant to be a gospel. Like if you use these palettes, we guarantee that they will be aesthetically preferable and discriminable. The data that I showed you are based on average judgments where every single participant judged a different set of palettes. So on average, they were as discriminable and sometimes more preferable than the industry standards. But that doesn't mean that every single color palette you get from it will be. And so that's just important to keep in mind. With great power to have flexibility comes great responsibility to use your eyes and thinking brain to not just use these tools by default, or I was gonna say blindly, that's the wrong word, but really think and look and say, do I actually like this? Is it doing what I want it to do for my visualization? Okay, so quickly, other things you can do. So I just mentioned this hue filter. So this is where you draw your hue filter. So I can just select a part of color space. Now I'm carving out the warmer part of space and just using mostly the blues and all the way to the purples. We can say generate, and we will see that it generates colors in that part of the space. Right now it's set by default to have a mid-level lightness so that it should create colors that are pretty visible on light and dark backgrounds. You can adjust that and you can play with that when we get into the hands-on component. If you want to get rid of filters, you press this little trash thing and it'll get rid of it. You can also add multiple filters. So if I want blues and oranges, then it gives me those 2 filters and it will generate using those. The other thing that's cool is you can set a seed color. So let's say you really like this particular cyan color. So you want that to be a start color. You can click that and it'll make that a seed color and it'll generate palettes around that color. If you don't want it anymore, you press the trash and it'll get rid of it. You can also put in RGB values for your own seed color. So let's say I wanted to do our Badger Red because I'm at UW-Madison. I can look up the color for Badger Red and put in those RGB values and then it will generate palettes around that. So that is your quick whirlwind tour of Cologorical. And so I think now we can hop into the hands-on component where you can play with these different features. So Danielle, you wanna take over now?
Yes, that sounds good. And I just so you know, Badger Red is upcoming in a couple of different ways. That's what you get when you get folks who overlap the same universities.
Go Badgers!
All right, awesome. So what I'm going to do now is I'm just going to do a quick walkthrough of Color Crafter. The links are both in the Discord and in the chat here. Thank you, Kath, for posting that. Also, if you want to, you are totally welcome to just open the notebook and have at it. I'm just going to step through how I created those colors in the notebook real quick. So as we get going here, you will kind of get a sense of how do I actually play with this thing anyway. So here is, where are we at here? There we go. And I also want to reiterate before we get going here, Karen's comment about with great power comes great responsibility, because that I think is one of the biggest things to keep in mind with these tools. There's no tool that is going to perfectly nail the aesthetics. That's something that I think is an open area of work for VIS, is how do we actually think about when and where and how these works all can happen in practice, and how do we scaffold and bootstrap? These tools are intended to scaffold and bootstrap. So I can tell you firsthand, Color Crafter will generate some really great stuff and it will generate some really awful stuff. So it is ultimately up to you to use these tools and adjust these colors in ways that reflect the properties that you want to see. So let me see, I think this will be the right window. Awesome, can you all see my screen? Perfect, so if we look at this notebook here, what you have here is I've loaded in the Eisenberg et al. VisPub data. It's a data set that many of us can relate to about publication numbers of different visualization venues. You are perfectly welcome to replace this with any data of your choice, but we use this just as a way of bootstrapping the next few activities. So when we're looking at Color Crafter, as I mentioned earlier, the basic idea behind Color Crafter is that we want to be able to generate effective continuous encodings. And when I first boot up Color Crafter, it will load a series of options that all have either a yellow or a very light seed color as just a means for, let's get something a little less bright, there we go, as just a means for generating a series and sequence of palettes that you can play with. So a few factors or features you might want to be able to adjust as you're working through with this particular tool is you can do things like rotate. So we have our curve plots here. This shows the path that the ramp is traversing through color space. And we can go ahead and rotate those to try and figure out what kinds of encodings we might desire. If we're working with a scatter plot, we might say, let's keep our colors a little bit darker, move our plot such that our very low values still pop out. Whereas if we're working on something like a bar chart, we might choose to adjust our lightness back up and give ourselves some nice pale yellows and pastel colors here. You can also adjust saturation. One quick caveat in here is this is not necessarily true saturation. This is saturation that is moving the entire ramp in the direction of the mean saturation of the curve itself. So if you think about the curve as a vector through space, we're moving perpendicular to that vector in saturation space. Otherwise, weird things happen. So that's why when I move saturation, you'll notice that some of my colors might change a little bit. I shift here from my purples to my reds by increasing the saturation. I get this kind of sunset-like ramp. That's a factor of the fact that saturation is going orthogonal to the vector traversed by the ramp itself. And we can also choose to reflect the curve to give us either cooler or warmer colors. One other feature that can be handy is for some of these smaller curves. These tend to represent ramps that are your traditional sequential encoding. So think of like your bluer blues, your brewer greens, and they may not traverse the full length of color space. You can increase the length of a curve encoding by using the color range buttons here. So you'll notice that the endpoints, the darkest point of the ramp gets pushed further away when I do that. So those are some of the basic tools that we have when we're working with Color Crafter. The other thing that we can do is we can go ahead and choose seed colors. So here I've entered the seed color FFD2D5. By doing that, I get this nice little mauve color here, this kind of very pale peachy color down to my lavender purple color. And this is the color that the color encoding you will see in our notebook here in our heat map. So what you'll see is for a heat map where we have these nice large marks, these kinds of pastel colors can generate a fairly nice effect. But if we take that same representation and we put it on a scatter plot where we have very tiny marks, these points here become really difficult to see, and it becomes very difficult to actually distinguish individual values, right? We've made our marks smaller, it's harder to distinguish between them. So one thing that we can do if we're working with Color Crafter is we can go ahead and we can push those encoding points apart, make it easier to see our general marks. I might have pushed a little far, there we go. Make it easier to distinguish between values in our general marks. And then we can also think about doing things like adjusting our saturation to get some nice bright colors that may show up well on these smaller representations. So as you step through this tutorial, that's one way to do that. The other thing that you can do is you are by no means stuck with a lavender palette. If lavender isn't your deal, totally fine. I'm gonna pull up a couple of different options or a couple of different seed colors here. So for example, Karen is at Wisconsin, and so as part of the handoff there, if you've ever tried to hand design a bright red ramp, you know, not the easiest thing in the world. So we can go ahead and we can add these seed colors and we can generate a set of ramps that all traverse through Badger Red, but they have slightly different ways of doing it. And those different ways can shift our design for everything from this more sunset style or more kind of, yeah, I guess sunset might be the right way to think of it. More sunset style, the yellow, orange, red, or more of our traditional light reds to dark reds. We could do the same thing. One of the nice things with Color Crafter is because the lightness structures are maintained, it makes things like, Karen, your example of an ugly color, which is awfully close to RCU gold. So go buffs, but not the easiest color to work with. But we can take these color ramps and these seed colors, we can drop them in here and start to figure out, all right, like I said, doesn't always do the nicest looking things. You have to use your own judgment in terms of what you want in terms of designs, but we can start to pick out some of these representations that might offer some desirable properties. And I'm going to adjust this curve length a little bit here, where we traverse through this gold and we still get a reasonably nice aesthetic structure that holds to the branding that I would expect out of CU. But I didn't have to spend days trying to figure out how to hack this thing into a ramp that was desirable. This can also be fun if you start looking at your Pantone colors. So if we come in here and we go to Pantone's color of the year, we can go ahead, pick that out and drop it in here. And we can get a series of different blue ramps that we can then play with. And if you get sometimes these ramps that don't look very good, but you like the general affect, this is where I would encourage you to play with things. So for example, here I have this green to blue, and I can say, well, that particular style isn't super desirable. But if I turn up the saturation a little bit, whoops, hopefully don't blow out the gamut, turn down the lightness a little bit, I start to get this kind of teal to blue affect that might be kind of fun when we put it on something like a scatter plot where we can see these points pop a little bit better. So as I mentioned, there is a walkthrough of spots to adjust these ramps to kind of play with Color Crafter on your own in the notebook. How you're going to do that is you're going to update the ramps that are specified in the Color Crafter and where is it? Color Crafter dark variables. And you can do that just by picking your ramp out of this hex list here. You can copy paste it directly, should work right out of the box. So I think that's all I have on that front. Let me stop share. Any questions there? All right, cool. So Karen, do we want to jump into the notebook play and let people play with that, or do we want to pause for a minute, go through the Cologorical activities, and then let people choose how they want to play?
This is where I would do a raising of hands of the room, but that's kind of hard to do here.
Well, I think we could do reactions.
Okay, yeah, let's do a reaction. Okay, do you want to? Okay, if you want to explore Color Crafter before even talking about Cologorical, raise your hand now. And the alternative I'm about to ask about is if you want to see how to use the whole notebook first and then just play the rest of the time. So option one is play with Color Crafter before seeing how to use the notebook with Cologorical. Raise your hand. Okay, alternative is use the notebook. Do we know how to raise hands? Okay, executive decision. Danielle, would you mind just going, oh, okay, we got one on that. Okay, good. So the alternative then is see all of the notebook and then just play the rest of the time. So hands down.
I think they just fade over time. There we go.
Okay, great. So let's take some time then to play with Color Crafter, and then we'll reorient to Cologorical after that. Thank you for your feedback, everyone. So Danielle, do you want to, or so everyone should have access to the link now because it's in the
Yes,
chat.
I think everyone should have access to the link. If anyone doesn't, let me know. It's in the chat and the Discord.
And so as you're exploring, feel free to mic on and ask questions or type questions in the chat. And we'll do this for how many minutes before we want to switch to Cologorical? Francesca, you can chime in too.
So I believe that we have until 2:45, and then because that's like 45 minutes, and then we'll switch over. So you guys should work out how you think is best. And maybe some people could, you know, I don't know if it's possible for people to post into the chat anything they've made. That might be helpful, and it might also be helpful if you like walk people through it, like, or show of hands. Can people get started on that notebook, or does anybody need help?
And also feel free to unmute if it's easier to do that than post in the chat.
And I will add, there will be a quiz at the end, so we want to results.
No actual quiz. There's no way to toss candy to the back of the room when people get something right. So we're gonna stick with just having some fun. Oh shoot, Color Crafter is blocked by Sandia security. Huh, that is a new one. Thank you for letting me know. I will definitely have to look into that. I can try and upload a version on my lab's website, which might get around that issue.
I can see it. You might want to check a different browser. I'm using Chrome.
Can I ask something? Would you rather we have our cameras on? Are you? Do you feel like we're talking to the void? It's up to you.
It's ultimately up to you on what you're comfortable with.
I love if you turn your cameras on, but I wouldn't ask you to do that if you're uncomfortable.
And Jonathan, it's a great question. How do I know if it's a good color ramp? I think we're still figuring that out as like a research area. Is what is a good color ramp? But I think there are those ramps that look really strong and really clearly like, okay, this is something that feels intuitive, that I can understand, that it's not like I look at it and go, mm-mm. And then there are the things that are horrifically ugly. Oh my goodness. Yes, please don't put that in anything. And then there's kind of everything in between, which I think is a really interesting, rich and sticky space. So that's kind of a non-answer, but.
As the artist in the room, I would say, oh no. I would say, how well does it fit your data and task and all those other things? Is it like that I think Aaron talks about associations, and that it's not a one size fits all. So it's not a good or bad color map. It's how well does it suit your data and your what you need from it.
Yeah, but we talked about earlier with these competing constraints. So you can end up in a situation where you have a lot of competing constraints that you're working with, and you just have to pick one. This happened to me recently where I was simultaneously writing a paper on the dark is more biased, and then I was writing a paper on leaf color preferences, and wanted to show that, and like autumn leaf colors were more yellowish and lighter. So then I had to like violate what I was arguing for in one paper to do something that I thought was better for communicating what I was trying to communicate in this other paper. And that's why I emphasize in my class, and also emphasize here, use your thinking brain. And not only your thinking brain, but the thinking brain of people around you. So if you are torn between how to navigate particular trade-offs for a specific visualization you're creating, ask your colleagues, ask your friends, and say, what is, like, how do you, like, don't give them a legend or label, say, what do you get from this? And ask them to describe it just based on what they see, and see which version gets them to the message that you're trying to communicate.
And I would add that all of these things are design problems, and that it is trade-offs. And if you want to have some difficult trade-offs, come see us tomorrow afternoon at our artifact-based rendering tutorial, where the trade-offs are like a fire hose, but the amazing possibilities. But it's always on that, you know, like, here's a simple rule and here's a complex problem, and you sit somewhere on that span.
It also,
I think when I teach my students, I find it difficult because it is a complex subject. It's very huge. It's got a lot to it, and I'm just firing out stuff that I don't quite really understand myself. And sorry, and then you've got the tools.
But
the tools are either sort of here it is, or you've got this really complex space. And I struggle between the two. Either the students just trust it, or I just trust it, or I have to really delve into this complex environmental understanding.
That's why we emphasized at this beginning the issue, so talking about perception and cognitive principles, so that if people can understand what is the ideas going behind these tools, they can actually evaluate based on the knowledge that they know about how the mind works, how they can evaluate the actual palette or ramp that they're getting. Another thing that I wanted to mention, linking back to what Danielle had said about the Colorado color. So although the dark yellowish color is least liked on average, color harmony, and not pair preference, but harmony is based on similarity actually also, and harmonious color combinations. If the colors are harmonious, then they are more liked generally. So even though people don't like that dark yellowish color on its own, if you pair it with a bunch of other colors in those ramps that Danielle showed, that is a harmonious ramp, in which case it won't be as disliked. So then it's not only, we don't want to just think about individual colors, we want to think about colors in combination. And preferences for color combinations is very poorly predicted by preference for the individual colors. But once you build in pair preferences, and that's what Cologorical does, then it does better.
And
So
I also think it depends on who your students are, because this is a complicated question. And if they're really learning, you know, to code, and they're learning to, you know, parse complex data, the last thing they need is, you know, 4 years of color theory and practice. And so we are really working hard at one, and the other of us, of creating simple tools that will just solve the problem for you. Because I work only with scientists, and I can tell you, they ain't making any of this stuff. It's like, give me an example, give me something, or I'm moving on. And it's not really fair to ask, because it is complicated, it's not really fair to ask, you know, for a really deep, complex understanding. And there are all these perceptual rules. And I work with Colin Ware, and what he told me was, he said, all the perceptual rules that we've been working on are individual. And I worked with Colin for 6 years. And he said, and then Francesca, she threw out all those rules, and she got things that worked. Well, that's just because it's a harmonious mix, but that's just because that's what I've been doing for my life. So it's not fair to ask people to understand these, and we don't have a clear enough understanding of all these disparate rules, but they don't apply in every situation. So we're working on recommendations, and they're not proven, but just examples and recommendations, so people can have a practical grounding. Here, try this if you got this kind of data. But it's a difficult problem, and I think we need more. You're right. We need more than the defaults, but we need less than you know, an unlimited number of options.
Great, so let's switch to the Cologorical part of the notebook now. So if you scroll down in the notebook that you are in, where you are working with Color Crafter, we've got qualitative data with Cologorical. And so these suggest a few activities that you can do, and you might want to do this on your own time because we're going to run out of time soon, but just to walk you through what we're suggesting you explore. So one is to explore changing those sliders. So you maximize perceptual distance and put the other two sliders down, name difference and put the other two sliders down, or pair preference. And then you can put in the different color coordinates here from that. Another thing that we have suggested doing was using those filters. So maybe get rid of those yellow and greens and see what happens, or maybe select one part of the space and another part of the space, and you can explore what parts you select from. And then explore dark backgrounds. So dark backgrounds are kind of all the craze now. And so here so as I mentioned, we have Cologorical by default give you colors that are in that mid-lightness range. But notice when we put this on the dark background, you can't see it very well, even though this is in that mid-lightness range. So you would create a palette, you would look at it and say, okay, I can't see that very well. Let me adjust the lightness range in Cologorical to give me a palette that is overall lighter. So you can explore that. And then here we suggest you exploring different seed colors, where you can put in your own colors that you want to design around and then see what it comes up for you there. So that is what we suggest that you explore. And I think we have about 4 more minutes to give you time to do that, and then ask Danielle and myself any other questions that you have, and then we will switch to Francesca's section. And welcome, Maureen.
I have a question. It might be silly though. Are you happy for us to use that in the classroom, like these 2 tools with our students?
Sure, absolutely. So you can use them to show what they do, and you can use them to explain issues of aesthetics and preference, and you can use them also to show where they break. So like I mentioned before, these tools are not perfect tools. So you might say, okay, what is this doing that maybe feels like it's not working? Or let's force it to do things that might not work, and then see if they don't look very good, and then why is that the case? So I absolutely suggest using these to the extent that they can help you with teaching. Have fun with it.
Thank you.
And I think Laura dropped a question in here about color tutorials or labs focused on geographic data. Thoughts?
We're working on that.
Yeah, I was gonna say, Francesca,
Danielle and I are working on that, and actually I work primarily with environmental data. So we have a new website coming out probably in about a month that will have a lot of recommendations on that kind of front.
And of course, Color Brewer was designed for maps, right? And so the thinking behind that is pretty interesting. A lot of that, you know, you get the challenges of the different size and the different surrounds. Surrounds ends up mattering a lot on that kind of thing.
Yeah, the thing that we're finding with a lot of geoscientists is that they're looking to layer and layer. So they want like a color map and then one on top with a different texture. So now you have to begin to look at the interaction of color quite closely. And Colin Ware and I did a paper on that, but we got a long way to go.
Yeah, layering's hard.
And with response to the papers that Maureen just brought up, I'll drop those in the Discord in case folks haven't seen them. They're great papers to read, definitely worth understanding what the theory is behind Color Brewer, given its prevalence in the community and all the cool stuff it does.
Cat.
Yeah, we've got about 1 more. Hello, Kat. I got mine. So we've got about 1 more minute. If there's any more questions for me or for Danielle, and then I think we'll turn it over to Francesca if I'm getting that timing right.
And yeah, the color session seems to be the session for cats to drop in. Mine is sitting in my lap right now, so. And do feel free to reach out to either Karen or myself after the tutorial ends. I think these are all the tools you're seeing today are tools that are systems under active development. There's a lot of really interesting and cool questions. And if we can help you out with things now, we're happy to. And if it turns out that's one of those questions that needs more work, I'm also open to collaboration and other kinds of forward investigation.
Wanted to throw out to you and Karen and Francesca won't be surprised by this. I'm finding that chroma contrast is got more to play, especially in gradients than our kind of classic theory says. And so I'm seeing, cases where I can distort the luminance order, but with the chroma, higher chroma, especially around the yellows, it feels okay.
Very cool.
So, as a nuance, as you guys keep working.
Thank you. Why is there a trend to a black background? Quick answer to that, I think two things. One is it's easier on the eyes. Two, it's new. And I think that if we were all about the black background for a long time, then I think there'd be a craze towards a light background just because it's something really new. But I do think the big part is perceptually it's easier on the eyes.
Oh, now Karen, black backgrounds were all the rage back before displays were light enough and bright enough.
It's all cyclical.
It is, and it's sort of easier on the eyes. We can argue about that over a glass of wine someday.
I actually don't feel strongly about that one, so we can not argue but have a informative discussion over a glass of wine.
It is important if the room's dark. If the room's dark, it's really nice to have a dark background.
Yes, I have strong feelings about backgrounds for presentations, but that is beyond the scope of our current topic. Yes. I'm all about white backgrounds for that. My students are laughing at me. Okay, what is the real issue?
See, people are...
Your white backgrounds on your presentation. I know somebody who has a strong feeling of the opposite. So he likes to only do dark on backgrounds on his presentations. But I feel like if they're going to print it out, it's going to waste a lot of ink.
And if you're in a light room and you're projecting onto a light, it's light onto light, it's harder.
I think we can all agree though, no royal blue backgrounds. Let's pass on that one.
I saw one of those recently. It was like a blast to like the early 2000s.
Ooh, did it have red text?
Yeah, and yellow.
Yellow. Now there was actually special films that would do those blues.
Francesca,
first time at SIGGRAPH.
Francesca, you're muted.
I try to stay quiet. CCC tool is actually quite complicated, so I want to make sure we have time to move on and get all the way through that one. And I have started a paper on backgrounds. I feel passionate about it. We'll pass on that one. So I'm going to go first and tell you a little bit, just like overview of how to run through color moves. And it's not to talk about the theory. It's really a practical, like, might this be helpful for you or your students? Maybe yes, maybe no. But I'm looking at sharing my screen here, and it says one participant sharing at a time. I don't know if there's anybody else sharing at the moment.
I don't see anything being shared.
You don't see my screen by any chance, do you? I clicked on the green button and I clicked on my desktop and I clicked on share. Oh, for crying out loud. Okay, so Pascal, why don't do you want to go first real quick through your movie and then let me change my preferences and find Zoom and figure out what the heck's going on.
Okay, so I have to start my movie by myself.
Who's in charge here?
So you clicked on the share screen? it's letting her share her screen, but it's showing her blank options for her screen.
All right, so so I'm going to cut out in case I'm the problem and let you go, Pascal, and then I will be back.
So again, the question, do I have to share my video by myself, so not the technician do it?
I think so. I think we're going screen share for this session.
Okay, I will try it. So can you see my screen? And I'm not sure if I also share my sound. So is everything
Yes.
okay?
We can see your screen and hear you.
We can't hear your video though.
Oh, you can't hear my video?
So if you stop share and you go to share screen, there is a button that's hidden in tiny text in the lower left that says share computer audio.
Okay. Okay, again, I will share my, maybe I have to, I click on share screen and then there are only two checkboxes. One is, oh yeah, now I have it. So we try it again.
Hello, my name is Pascal Nardini. I'm from the Leipzig University.
Perfect. Okay.
With this video, I want to give you a little overview of the CCC tool. Before we begin with the tool itself, I want to explain short the color map specification CMS we developed for the tool. The CMS consists of keys. A key is defined by the reference value X and two colors, the left color CL and the right color CR. With different combinations, we distinguish between 5 key types. First, the nil key. The nil key has no defined color and we use it to initiate a constant band at the beginning of the CMS. The right key has a defined color for the CR color, and with this key we initiate a scale band at the beginning of the CMS. One color for the behavior within the CMS is the dual key. Here both colors are defined and both colors are also equal. This key causes a continuous transition within the CMS. In contrast, a twin key causes a discontinuous transition. It had also two defined colors, but the colors are different. Behind the discontinuous transition of a twin key is always a scaled band. If a user wants a constant band after discontinuous transition, he has to select the left key. The left key has only a defined color for the CL. Next to that, the left key is always used to end the CMS. At least we modified the key definition, though that the user can set a color for the exact value X at discontinuous transition points. We use an extra color CM, which is equal to the CL or the CR color. And now we switch to the tool. If you open the ccctool.com, you will see this page. Here you can select between different tool variations, but at the moment only the CCC variation is implemented, so we select this one. After loading screen, we are at the welcome page. Here you can start with the button begin, or you can scroll down and get a few information. At the bottom of the page you can see the version number. At this video we work with the version 0.902. Back to the top, at the text under the buttons, you get the information to open the navigator with Ctrl and M. You can always open this window at any section of the tool using the shortcut Ctrl and M. The navigator map shows you the structure of the tool. You can also use it as an alternative way to transfer from section to section. The blue button with the smiley is your current position. Dark gray buttons are sections which can be visited, and the whiter ones are sections which cannot be visited from your current position. To close the navigator map, use again the shortcut Ctrl and M. And now we start with the begin button. This button transfers you to the My Design section. Here you can see a red pop-up window which inform you that the current design of the tool is in early access and some features are not entered to the system now. At the My Design section you can manage up to 10 of your designed CMS. But first let us start with a CMS and I will explain the functions of this section later. The tool offers two methods to start a CMS. You can choose a predefined CMS from the gallery or you can create a new empty CMS. First, I will show you the gallery section. Here you can find all predefined color maps which are a contribution from the skywizcolor.org. At the bottom of the page are 8 buttons. 7 to separate the color maps into themes and 1 to go back to the section where you come from. Each color map is also equipped with 4 small buttons at the right top corner. The first will create a reverse version, the second one is for the export, the third one to add the color map to the My Design section, and with the last button you also add the color map to the My Design section, but you switch directly to the Edit section. We select the third button and are back to the My Design section. And now let us also try the second method and start a new empty CMS by clicking on New. At the new page you can set the name and the interpolation space. But you can also change these settings later at the Edit section. Next to the freestyle option we also want to work on a more auto-generated way for the CMS creation. But this is part of the future work. With clicking on the Create button, the tool will reserve a slot at the My Design section and we switch to the Edit section. This is the heart of the system, where you can edit and analyze CMS. At the left side you can see all predefined CMS from a gallery section and above them containers with a single color. These are elements you can drag and drop at the top, middle and currently free area. I will do this with a divergent predefined CMS and 2 single colors. You can see that we have here 2 visualizations of the CMS. The top one is a standard linear illustration and the bottom one is the band sketch, which has equal width for all bands. This is important if a CMS has small sub-areas which you can't see at the linear version, like for example this. Above of our created CMS you can see a bar where you can change the name, the interpolation space and type, the special color for non-entries, the color for values below the CMS range and the color for values above the CMS range. At the left side of this bar are the warning signs. The current one shows us that we have unsaved content. At the right side is a double arrow which opens an additional bar with buttons for faster interacting. Here you have the options undo, redo, save, export, clear, scale. To create a reverse, switch on the add modus, the remove modus, and to cause equal distances between the keys. If we click at the plus button, you can see left at the bar a red plus sign for the activated add modus. Then if you hover the linear color map illustration, you can see a new key. With a mouse click, you can set this key to the CMS. We switch to the remove modus with the minus button. Now you can see a red minus as warning sign. With a mouse click on a key on the linear color map, we can remove the key. If you finished your work, you can go back to the normal modus by clicking again on the minus button. If the keys in the linear illustration are too close for the remove modus, you can remove them alternative in the key list on the right side of the color map. The first and the last keys are fixed, but if you select another one, a delete key button appears and you can remove the key. Here you can also set an exact value for the reference value of the key. If you click on change value, a small window appears and you can change the reference value. At the window next to the key list, you can edit the key. You can change the color and the key type. I hope you remember them from the beginning of the video. For changing the color of a key, just click on the related segment of the key illustration. This is a dual key, so here I can only change one color. In contrast, at a twin key, we have 3 segments. Click on the right or left segment and a color picker appears where you can select a new color. With the top segment, you can change the middle of triple color. The tool always shows you the possible options to change the key type. So for the first key, the kneel and right key, and for the others except the last one, the dual, twin and left key. To change the key type, just click on the button. Below the key types is a button where you can set the key as burdock key. If you click on this button, a small red rectangle appears below the key in the linear color map illustration. If you move this red rectangle with the mouse, now the full segment until the next burdock key will rescale to the near key position. In contrast, if you move the same key using the key rectangle, only the position of the key will change. Another way to change the color of keys and also to analyze the CMS is to use the path plot. The path plot is separated into 2 areas. Left, a 3D version of the selected color space with a drawn color map. At this area you can use the mouse to zoom, to move or to rotate. This 3D plot supports the interactions at the right area with a better imagination of the color map path through the space. At the right side you can see a top view of the selected color space and 3 line charts of the color space components. A special statement for the RGB color space. Here the right side consists of a 3-side view or only the light charts. The light charts can help you, for example at the HSV color space, to control the process of saturation or the lightness. You can also work at the uniform color spaces lab and D99. For the illustration of the color map path we use different components. Continuous sections of the color map are circles connected with a solid line. These circles are interactive and represent the key colors. Discontinuous transitions are illustrated with a dashed line in the top view and with no line but 2 elements in one column in the line charts. Constant bands are rectangles in the top view and 2 connected rectangles in the line chart. If you move a color in the top view, the background updated to the current lightness level of the selected key color. In the lab and D99 space, it also shows all colors for the lightness level, which can be converted into the RGB form. The path plot color space is independent from the selected interpolation space, so you can compare how the color map path will change with different selected interpolation spaces. You can also compare how the color map would look like with different interpolation spaces. Therefore, you have to use the menu bar to open the analysis. By the way, you can also use the CMS button at the menu bar to use all the edit methods we used at the fold-out bar above the color map illustration. And there are also shortcuts which can be displayed under Display and Show Shortcut. Okay, back to the analysis. Also under Display, you can select Show Analysis. At the analysis, the first point in the select box is the interpolation spaces. Here you can compare how the color map would look like using RGB, HSV, Lab or D99 for interpolation. You can also change the illustration type between linear plot and band sketch plot. The next point is the analysis of the local uniformity. Here we have 2 options. The speed bands, which use the speed information calculated out of the color difference and the distance of the key reference values. The speed bands give you an overview to compare the local uniformity of all techniques to calculate the color difference. At the local speed plot you can only select one type, but you have additional the statistics, and if you work on the color map you can better focus on, for example, D99 Euclidean distance. At a global speed plot you can select continuous sections of the color map and can check them for global uniformity. You can use only the color information or you can add additional interval colors between each key pair. At least the tool offers the intrinsic order plot. Here we combine the local and global intrinsic order in one plot. Blue bars at the top show you the positive values for local intrinsic order values and red ones the negative ones. The first red bar is okay because it's not happy with the dark blue color between the purple constant band and the other blue key. That's okay because with the purple constant band we maybe want to highlight very low colors, but we can do something against the second red bar. Here the intrinsic order is unhappy with the sign color. It has too much deviation from the neighboring blue colors, so we move it a little bit closer to them. At the bottom you can see only the negative global intrinsic order values. The color of the lines show you with which color it is unhappy, and the start and end of the line show you the related colors which were used to calculate this negative global intrinsic order value. And now we have finished the edit section. At the menu bar at the bottom are 3 additional modi: optimization, color blindness simulation and probes, but this would be too much for our overview video, so we save the CMS and go back to the My Design section. Here the CMS is also illustrated with a linear color map and a band sketch option. At each color map container you have the options to export and delete the color map. If you want to save the full session, you can click on the export button at the menu bar. With the import button next to it you can load single CMS files or session files. At this menu bar you can also reach the testing section where we offer a few interactive test functions, but this is also not part of the overview video. At least I want to show you the export page. We click on the export button of our custom CMS. At the export we offer the file formats XML, JSON, CSV or images of the color map. You can export only the key colors or with additional interval colors so that you will not lose, for example, the uniformity attribute of the lab interpolation when your application will only work with RGB colors. Some applications also have problems with our discontinuous transition points where 2 colors have 1 reference value. Then you can select handle twin issue and the tool will add a small value to the reference values of the second colors of twin or left keys. And this is the end of my little overview tutorial. I hope it was helpful. Many thanks for your attention and goodbye.
Yeah, I hope it was not too much and not too fast, but it was a lot of content for 50 minutes. Yeah.
Yeah. So what I can tell you as someone who's used the tool a lot is it's an incredibly powerful tool with a lot of controls and a lot of perceptual fine tuning. So, but again, it's really tailored for someone who needs very specific things because it is a little more powerful and complicated until you get used to using it. But I don't use anything else for constructing color maps, but then that's all I do. So what I'd like to do is I'd like to, because we are getting a little short on time, I'd like to go ahead and I'll show you my tool's much simpler. And one of the focuses of the that what we really wanted to convey was, if you have this kind of a task, here are the tools you could use, or if these are your goals, here are the tools you can use. And so I think that Pascal's tool is good if you are really looking for a finely tuned map that's tuned to specific data ranges or whatever. It's very powerful. What I'm going to show you is something that we made very specifically as an easy tool to use. It's called Color Moves, and it's a drag and drop in kind of thing. And so I am still having some challenges, but I'm going to try this again. And I'm going to try and share it again. Oh, 62 is perfect. Oh, we're in good shape here. Hold on. Fate shined in my direction. But, oh, for crying out loud. Okay. All right. Pascal, why don't you take questions? I have to shut off and turn back on, and then I'll be able to share my screen.
Okay. So does anyone has questions about the CCC tool? Maybe I have to open.
So Pascal, it looks like there's one in the chat from Fareed about, can you change the opacity of the color map?
No. we designed the CCC tool only for 2D data because we want to, so if you use opacity, transparency, and also want to analyze the perceptually uniformity, this is a very hard task. So I'm not sure how we could do that. So we started only for supporting the 2D data. And yeah, so we decided to not support transparency.
Okay. Any chance my my screen is?
Looks like it's working.
Okay, well then let me find the right window. Oh my God, I've got so much going on here. Okay, so I really I'm going to run through this quickly because I really think that just having your hands on stuff is kind of the best way. And so what I think I'm just going to give you, I'm going to skip all the theory. Okay, and so this is what you're looking at. And I'll even show it to you in presenter view if that would be helpful. No, never mind. You don't get to see presenter. Is it big enough? Yeah. Okay. So this is the interface for color moves. That's all of it. That's all you get. And there are the only things there are only 4 little buttons that you're going to need to know about. One is separates your color map, one inserts something in it, and one exports it. So what I'm going to go down here is, this is the process. Okay, this is what I call it the magic color map, but it's not really a magic color map. It's a color map whose RGB values link to the values, the data values. And that enables you to, I'm trying to click and paste this into the chat so that you guys can link onto this. But if I could find the chat, that would help, but oh well. I'll get you there. So, so what happens is you apply this color map to your data, okay? And you can do that. We've got it. You can download it. It's just literally applying it to your data. And then all you need is a PNG. And you take the PNG and drop it right into the interface window, okay? And then you'll see your data. And then you've got the list of color maps, and you've got a histogram that shows the distribution of your data. And you can start sliding the pins, adding color maps, and all kinds of things. So, and once you find a color map that you like, you can export it, which is the export button. I'm going to demo the tool for you because I think that'd be better. You can export it and upload it into, you know, I use ParaView, but whatever your tools are. So I am going to just made you a nice PowerPoint, but we're skipping it. Okay, so this is, so the site is sciviscolor.org. And then here, I'll even go back and you can see. So this is our home page. It's getting a major revamp. Won't look like this in a month. If you go to color moves, and then here you can, hey, come on, you can grab, see how I'm grabbing, and just put one of these on your screen. So just grab one, drop it on your screen, and you'll be able to play with it. I don't recommend the one on the right. It's not as, it's got some other quirky issues. And once you have one of those on your screens, just let it sit there. Oh, here we go. And open up the window. It's on the right. And you're just going to take that and drag and drop it right on in. Let's see. So this is the one we often demo with because it's so beautiful and it's pretty easy. And you can, so you can add solid colors and make it really ugly. You can just drop and drag your things. You can turn them over and say, oh yes, that's better. We can say, okay, nobody really wants to look at that. Okay, we can move our pins around so that it emphasizes certain data. We can say, well, okay, I guess that data really is important. There you go. And then if you want to start something new, you just say, hey, give it to me again, please. Okay. And so what I want to do is I will choose, oh, I had something in mind. Okay. So the other thing that happens is, let's say you have time varying data. Okay. So we can add, oops, more views or more time steps at one time. And this has a lot of advantages. So often when I'm starting, I just start with something really basic. And then the first thing I want to know is, where's my data range? What is important? So I take this beautiful pink up here and I drop it in there and I say, oh, there is something there. Don't think it's all that important, but let's just figure out where my data range is on this side. Oh, I'll try this green guy. Oh, okay. So now I know I've got some on there. Let's keep those little waves going and just have it there. Okay. So I don't really want pink. And being, you know, aesthetically erotic, I'll go with that. So then I'll say, okay, now what have we got? All right, well, so I can tell you what I know from the scientists is that they're interested in seeing the detail here. They're interested in seeing these, I call them the wing waves, and they're interested in seeing the bow fronts, which you can't see at all, which are right here. But if I take a pen and I say, okay, I really need to see those bow fronts, people, so help me out. What happens? Oh, okay, so now I can see them a little bit too much, a little too glaring, right? But as with my normal principle of a little goes a long way. Oh, I did this. I tried this out for myself and it worked. You could see the bow fronts. So maybe, here we go. So you can see how by sliding it, I can get detail in the waves. But what I want to do is I want to balance the detail in the waves along with the detail in the bow fronts. And there are my bow fronts. So I know from having talked to the scientists that this is what they want to see. So now all of a sudden it's a very specific map. And it's certainly not going to do for all purposes. But what I do have is something that is tuned to the scientists' needs, okay? And what I've found is that they spend a lot of time, I find it very helpful in terms of exploring their data because they can explore really small features and small changes. So a few other features, you can put in what is the actual data range of your data. You don't have to stick with just a percentage. You can insert a color without disturbing the underlying like linear distribution. And then look, you can see it, it's right there, right? And you can make it bigger. So if you want, if you've got, for instance, a specific, like I want to highlight, 73.6, then now I know, oh, there's 73.6 right there. And I can move it around and I can get a really close up look at what's going on. The other thing I can do, because sometimes the data range is really specific, is I can drag in here and I can say, no, come back, wherever you are, come back. There you are. Now, I have found that finding features in these large data sets often means, it could be like 1/2 of 1/10%. I mean, it's just minuscule differences. And so this change, like this is 56, 57 is somewhere over off the screen on the left. So you can see that that's a very subtle change, but it makes a difference in what you see. And the other thing that goes on is now all of a sudden, let's say we're going to just reset this because it's kind of wacky. You can also set priorities. So this is, these are 3 time steps of one data set. And you can load them separately. Oh, isn't that gorgeous? You can load the time steps separately so you can see all 3 histograms, but I was making it easy for us here. So I don't have any idea what I've got here other than I know it's a kaleidoscope. So when I don't have any idea, I throw things on and say, okay, I wonder what's going on where. And I know that they're interested in tracking this feature. This is the early, mid, and late time step. I know that they're interested in tracking that feature, and I know it's in the blue. So what I'm going to do is I'm going to flip that color map around, and I'm going to drop it in there. I'm going to say, okay, I need a little more help in there. So now you can see I've gotten the detail that I was looking for there. The rest of it's a little bit garish, but we'll worry about that in a minute. I've lost some of the detail in this middle step, but that's because it's gone over here, and I see where it is in my final step. Okay, so that's the use of this particular, of this, you know, like that's the use. But now this is a mess, and it's red, green, God forbid. So we don't want to do that because that's a colorblind issue, right? So I'm going to flip it around. I'm going to drop my blue in, and I'm going to get rid of my green altogether. Say goodbye, green. We don't want you around. And this guy is just non-existent anyway. Okay. So now we have, which you're used to seeing a cool worm, right? But you can see where it, you can do a few other things. Like, for instance, if you want to emphasize the red more, do you see this little red button down here? I call it a radio button. If you've got a color map, you want to get rid of the white. Okay, so oops, the white's gone. Okay, or you want to get rid of the dark because it's too sharp of a contrast. Okay, there it's gone. And so it's very flexible, and the results that you'll get are very flexible. And the other thing, if you're looking for, so let's say my data range here really is, oh, I don't know, 40 by 1200, you know, I don't know, whatever it is. But what I want to say is if you're wanting to know, oh, where is that? You can see the green line, and it'll tell you exactly. So that if you want to set a pin, it's going to pull out specific features. Like if I decide that area next to the red, I really want to highlight it. Okay, I'm going to take my pin and I'm going to drop it in there. Well, obviously I don't want blue, but maybe I want this color that no one likes, but I love, because see how nicely it offsets that. Okay, so yeah, there's some overlapping hues in here with, I'm not saying by any means stretch of the imagination that this is a good selection as an end color map, but I was just kind of showing you what the capabilities of the tool are. And then there are a couple other things to know. If I can come on over here. So here you can, so now you've got a color map, you can save it as an XML, a JSON, you can save the JPEG, no problem. And you can also, I do a lot of work with three-dimensional volumetric renderings. So for me, being able to control the opacity of specific hues. So here I can control ranges of the opacity. So now all of a sudden I've got the differentiation that the different linear ramps give me, but I've really highlighted, you know, this area that they're interested in. It's combustion data, so they want to know what's really burning. And the last few items, if you hover over the center, you can save it. It says, okay, we'll save it. You can say, send it back to its original size. You can say, make it 100%. And then, oh, last thing. So I am sure that there is no one else on the planet with as many color maps in their, on their computer as I have. But if you're like me, and you have 1,000 and you think, oh, that I don't really, I know I have 11 blues here, but I think I need a different one. Then all you have to do is take an XML or a JSON or whatever you've got lying around and drop it in there, okay? And it will show up here at the bottom. And so, 3 ways. This is one that I actually made in CCC tool. Okay. And did it go in? Hey, you. Yeah, it's got a lot. Oh, there it is. So I'm gonna get rid of this stuff. Say goodbye. Then I can pull up my little guy back here again. Where did you go? These are all my little float files. We'll try something new. And sometimes when I'm just, a lot of times these data sets are really, really big. Oops. And I need to just do some exploring. So, where did my cursor go? So that's when I often try something like this. And I say, okay, well, we know there's squat here because that's what my histogram tells me, or maybe I'll put it in my pink because that way I know I'm really not seeing anything there. And I'm going to say, I'm not sure what's important here. And I'm going to put in the red so we'll know. Oh, there's some red on the edges. So I happen to know that, so you can see if you are looking to figure out what the heck is going on in there, because a lot of the scientists I work with, I say, well, what do you want to see? And they say, well, I don't know. I don't know what's there. It's like, dude, you just ran a simulation that took a month to run. What do you mean it's not, you don't know what's there? But it's true, they don't. That's why it's research. But so what these guys are interested in are, is the coastal region. And so this enables them to say, okay, I'm going to concentrate my contrast, because it's always all about the contrast, right? I want to concentrate my contrast. This is actually bathymetry. And I'm going to not show, oh, isn't that much better? And I'm going to say, where are the low lying regions within Antarctica? And there they are. So it's a really simple to use. There are not too many bells and whistles. You can drag in your own things. What you can't do is manipulate the color maps themselves inside, but there are other tools to do that. And there are discrete colors up at the top, as you might have noticed. So the concept is a really simple tool for folks to use to construct and then export for use in whatever the tool is that it's going to apply. We actually have it hooked up to pair view, so you can do like 3-dimensional things and move them around, but that's not quite ready for prime time. So let me copy for you. I have, I did put, well, on the website, it's cybersecurity.org, there are some files, float files to experiment with. Well, let me go back and I'll just show you the directions a little bit. So questions, anybody? And you need to like unmute yourself and talk to me rather than put them in the chat, because I can't do 2 things at once. Is that pretty clear? No questions. Wow. Okay.
I'll kick off.
I'll figure out how to unmute myself. I'll go ahead. Can you hear me?
Yes.
So I absolutely love this tool. I've already started playing with it and using it.
Great.
Somebody was answering my chat questions on how to use it, and I think I figured out pretty much everything I need to know to use it successfully. And I want to be on your testing list for the pair view stuff. So I just want to say it's perfect for me.
So you know what? I can't tell who's speaking because
that was Brad.
Oh, Brad. Okay, we are on it. You are on our list. Stephanie, meet Brad. Stephanie Zeller is my partner in crime. And we are also, so it's a very flexible tool, and I'm glad you were able to use it, and I'm glad it was helpful. And I have, the attention span of a gnat, so I had to have a tool that would accommodate that. But scientists also, they're just so busy. So just a brief look at, so this is the color moves tool. We've got all kinds of color maps because that's just who I am. I can't help myself. We've got all different kinds of color maps, and any of these can be loaded into color moves if you want to, combine them or play around with them. We've got a gallery, we've got publications, we're working on a recommendation system. So this is color moves. And there are some examples, there's starting points. The biggest question I get from people is, wow, that was really cool, and I love watching you do that. but I didn't know where to start. So we also have a whole section on color sets, and that is literally they're jumping through the hoops on updating the website because it's about 100 pages. But we provide color sets that if you have data, this is an older one, but it's quite beautiful. We say, okay, your most important data should go in red. Your least important data should go in brown. If you've got something small, you need higher saturation. So that's the saturated green. If you've got something background that's more important than the brown, but less important than say the red, you got the green one. So we put together these sets. And of course, I know there's a red-green colorblind issue here. Although we find that if you're working with different value ranges, it's not quite so important. But so there are also recommendations and all kinds of things like that. Okay, and we really did set up for you to be able to test things, but I think we have hit the end of our time. Am I right about that? Anyone? Okay, well, even if we're at the end of our time, we have 10 minutes. So anybody has questions from anybody, from Karen, from Danielle, anybody, I think maybe, so my contact information is really easy. If you go to cyviscolor.org, our emails are on there. And I will post mine in the chat when I find that window. You're welcome to call me, or don't call me. You're welcome to email me if you have any questions or need any help getting started. We are always looking for folks to help us with feedback and with data and what they're using it for.
To Fareed's comment in the chat too, is this available? So I think all the talks are being recorded and streamed, so you can replay the entire tutorial, skip to whatever parts you'd like at your own leisure on YouTube. And like Francesca said, feel free to reach out to any of us at any time. We're happy to chat, happy to support. Any thoughts and feedback, it's completely welcome.
Email, don't call.
Yes.
Yes, yeah. And we're always looking also for people. We do a lot of color studies. Anybody who's willing to give us 15 or 20 minutes just to help us get some feedback, drop us a note. We'd love it. Okay.
And also the notebooks and several of the other materials are available in a folder that we can, I think, share. I don't think it's linked anywhere right now, but I can definitely drop it on Twitter and elsewhere if that would be helpful. Also, feel free to shoot us an email and we can share there as well.
Yeah, and the one last thing I want to tell you about Pascal's tool, so he did a beautiful job of making an exercise for you to walk through. It's right embedded in the tool. And so if you're interested in fairly complex maps, that's worth a look. Okay. All right. Well, have a great day. I know there are tons of stuff coming up. Everyone is still hanging out, which is, so if you have any last questions, we're here, but otherwise, have a great rest of VIS.
Thanks, everyone.
Thanks.
Thanks.
Thank you.
Bye.
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 Ecosystems are complex and dynamic. To investigate the dynamic nature of ecosystems, we have developed a prototype of a visual analytics system based on empirical dynamic modeling, EDM. EDM is a set of analytical methods rooted in nonlinear state space reconstruction. Integrating EDM with dimensionality reduction, brush-linked visualizations, and visual summarization support understandings of ecosystem dynamics.
Visualizing streaming of big data may be difficult if the visual idiom gets cluttered. Although some techniques solve this issue by aggregating data into different idioms, each representing a different period, they still lack transitions to help people understand how data points get from one visual idiom to another. To solve this issue, we proposed several transitions between several pairs of visualizations. We tested them through a user study where participants watched a video per transition and had to answer 7 questions.
As commonly known, dimensionality reduction techniques and their interpretations are complex, biased, and uncertain. In drug design, this highly complicates the search for similar and new chemical compounds. To overcome this issue, Canva brings comparison of different molecular descriptors and properties into one tool, featuring planar, 3D, and table views for evaluating the trustworthiness of high-dimensional data projection.
We propose X-matrix, a novel method for random forest interpretability. From a random forest model, a logic rule is extracted from each decision path on every decision tree. Once the complete set of logic rules is obtained, visual representations can be built for global and local explanations. X-matrix, making random forests interpretable.
Data videos are quite popular nowadays. They usually show changes in the data. However, creating a data video requires multiple skills, and the process is usually laborious and iterative. Our approach focuses on automatic and interactive visual enhancement of important changes in time series data with data video.
How do we represent remote users in synchronized visualizations while supporting divergent exploration? We present cursors, the basic unit of user representation in a collaborative visualization. They can vary significantly in appearance, as you can see. Cursors enable collaborative interaction techniques, such as peeking, tracking, and forking. To learn more, please read our paper representing real-time multi-user collaboration and visualization.
The success of convolutional neural network has been attracting many students and practitioners to learn the exciting technology. However, for beginners, the CN model is not easy to understand. We introduced the explainer, an interactive visualization tool to help beginners more easily learn about convolutional neural network. Using the explainer, users can progressively explore the CN model with real-life images in their browser, getting a comprehensive understanding of both high-level model structure and low-level underlying mathematical operations.
We have seen many visualizations for tree data structures, but when showing changes in trees over time, some focus on displaying hierarchy, while others highlight their changes. With split streams, we combine two approaches and their individual benefits. We evaluated our method in a user study and consider it a general-purpose method for the visualization of dynamic hierarchies. Our JavaScript library is openly available.
CMed is a visual analytics framework for exploring medical image data annotations acquired from crowdsourcing. CMed can be used to visualize, classify, and filter crowdsourced clinical data based on a number of different metrics such as detection rate, logged events, and clustering of the annotations. CMed provides several interactive linked visualization components to analyze the crowd annotation results for a particular video and the associated workers.
Drjs is a JavaScript library for dimensionality reduction where we implemented 11 DR methods. A typical use case for Drjs is a web tool using DR. You just need to import Drjs, create a DR object, and then call the transfer method. That's it. See the talk, the paper, or the supplemental material for more information.
Magnetic reconnection is a ubiquitous and complex physical process that occurs throughout the universe. Locally, this process is observed when the solar wind interacts with the Earth's magnetosphere, causing magnetic field lines to break and reconnect. One of the results of this process can be seen from Earth as the aurorae. In our talk, we introduce scalar field topology as a method to identify and analyze features in 2D magnetic reconnection simulations.
Transitions are widely used in data videos to build seamless changes between video narrative. As the attention cue, they can not only keep viewers oriented but also express narrative information. After conducting a content analysis on the transitions in the dataset, we provide a comprehensive taxonomy of narrative transitions in data videos.
This is a picture of a Tableau visualization within the browser. The data behind the visualization does not exist here, and Tableau is not running. This is just an image. However, parts of this image are fully interactive. Please join our presentation to see how we can share interactive visualizations across the web, free from any dependency on data or visualization application.
A testing environment for continuous color maps. Many other fields in the computer science do it, we should do it too. With our work, we introduce the approach of using test functions as a standard evaluation method. We present a test suite for continuous color maps implemented in the CCC tool. Adapt the task to your requirements at the interactive testing section and observe them at the testing evaluation section.
Information about vulnerabilities helps defenders prioritize what they need to patch, but this information can be difficult to interpret. In this paper, we support interpretability using a focus and context approach to visualizing vulnerability data, including a cluster